There is something moving out there, an object not born of our sun yet now circling it in a slow, shimmering arc of heat and dust. We can't see it anymore. The light of our star has swallowed it whole, hiding it behind a curtain of brilliance so intense that even our finest telescopes must look away. But the instruments keep listening. Numbers stream in. Silent coordinates shift. The object is still there somewhere, on the far side of the sun, completing a journey that began before our species ever looked up and wondered. If these mysteries have you on edge the way they have me, don't just watch Join the Hunt. Hit like and subscribe so you don't miss a single revelation as this story unfolds moment by moment in real time. Tell me in the comments where you're watching from, what time it is there, and whether you believe we're hearing the whole truth about what's unfolding above our heads. And if you want to keep the signal alive, share this video on X, Facebook, Reddit, or even just with the people who still look up at night. You are the reason we can keep following the impossible, and for that, thank you. We call it 3I Atlas, the third interstellar object ever confirmed to visit our solar system. It's an unassuming name, almost bureaucratic in its precision, but behind it hides something astonishing. This is not a body native to our neighborhood. It does not belong to the planets, the comets, or the countless icy remnants that orbit our sun in familiar ellipses. It comes from elsewhere, from the dark between the stars. To grasp how rare this is, think of our solar system as an isolated island chain bound together by the gravity of a single star. For billions of years, debris from its own birth has cycled through the same paths, falling inward, burning out, flung back again. But 3I Atlas is a drifter from another shore, a fragment of a distant planetary system that broke free of its own star and wandered through the galaxy for untold eons before crossing ours. The odds of such an encounter are infinitesimal, and yet it has happened again. The first time humanity recognized such a visitor was in 2017, when the elongated tumbling object Oumuamua flashed across our skies. The second was 2I's Borisov in 2019, a classic comet seen through the telescopes of Crimea. Now comes Atlas, discovered in 2025 by a network of telescopes, whose very mission is to scan the heavens for potential threats, asteroids, that might someday collide with Earth. Ironically, this one poses no danger. Its path will never come close. Yet in a deeper sense, it still strikes at something essential, our certainty that the solar system is a closed, well-understood place. Right now, Atlas is invisible to us, hidden behind the sun's fierce glare. But before it slipped away, it left clues, light curves, spectra, polarization readings like faint footprints in cosmic dust. And these traces reveal something both familiar and alien. It behaves partly like a comet shedding gas and dust, forming a hazy coma. But it also defies expectations, glowing too early, scattering light in the wrong way, spinning through space as if it were built from ingredients foreign to our own. So what exactly is 3I Atlas? A comet from a frozen world, orbiting a distant red dwarf, a shard from the ruins of a shattered planet, or as a few voices whisper in late-night observatories, something designed technology mistaken for stone? Science does not deal in whispers, but in evidence. And in evidence, the line between natural and unnatural can sometimes blur. What we know is that 3I Atlas moves too fast to be bound by the sun. It is here only briefly skimming the inner system before leaving forever. In that brief visit, it becomes a message in motion, a piece of another system's history carried across light years. Imagine it a fragment older than our world, drifting through interstellar night for billions of years. No star to orbit, no heat. Only the occasional brush with the faint gravitational tides of passing suns. It may have crossed clouds of dust where stars were still forming through nebulae lit by the deaths of others. And somehow, by pure coincidence or cosmic design, its path intersected ours. The scientists who first noticed it didn't look for poetry. They saw data points, motion vectors, a streak of pixels across an image. But as they compared observations from Hawaii, Chile, and South Africa, the pattern emerged. The object was inbound from beyond the gravitational reach of our sun. That realization struck like a quiet thunderclap across the scientific world. Another messenger from the void had arrived. Interstellar. The word itself feels almost impossible, something that should stay inside the pages of science fiction. Yet the evidence is plain. Every measurement, every velocity calculation tells the same story. Atlas is not of us. It is merely passing through. And so, as it disappears behind the sun, we wait. The instruments are silent now, but soon, when the Earth swings around its orbit and the glare subsides, It will re-emerge in December's sky. The world's observatories will awaken again, hungry for data. But before we chase what comes next, we must retrace how this story began, how we first saw the faint glimmer of a stranger crossing our cosmic doorstep, and what it might mean for everything we thought we knew about the boundaries of home. Because sometimes to understand what visits us, we must first understand why we are watching at all. Perihelion, the solar crossing. Right now as you listen, 3EI Atlas is nearing the point of greatest intimacy with our Sun. The perihelion, the moment when its long open-ended orbit swings it closest to the furnace at the centre of our solar system. On October 29th, it will graze past at a distance of 1.4 astronomical units, about 210 million kilometres. If that number feels abstract, imagine this 1 astronomical unit, or 1 AU, is the average distance between Earth and the Sun, the yardstick by which we measure everything else in our cosmic neighbourhood. 3 Atlas will never come close enough to scorch or collide. It will remain roughly halfway between Earth's orbit and that of Mars, near enough for the Sun's radiation to wake it, but far enough that even the most powerful telescopes on Earth can't see it through the dazzle. Perihelion is the moment of transformation. Every comet has its personality, and this one's begins to reveal itself here in how it reacts to the light. For billions of years, Atlas has wandered the deep cold of interstellar space, a block of mixed ices and minerals so frozen that atoms themselves vibrate in slow motion. Now, for the first time in perhaps 5 billion years, sunlight is touching its skin again. Imagine standing on its surface, if you could call it a surface. The sun would not appear gentle or distant as it does from Earth. It would be a blinding, relentless sphere 3 times larger in the sky, pouring out not warmth, but radiation. The vacuum offers no comfort, no breeze to carry heat away. Photons hammer directly into every grain of dust, every crystal of ice. The frozen gases, water, carbon dioxide, methane, ammonia begin to stir. They do not melt in the normal sense. Out here, there is no air to hold a liquid phase. Instead, the ices skip straight from solid to gas, erupting outward in tiny jets. This process is called sublimation, and it is the beating heart of a comet's life. As sublimation begins, Atlas awakens. Gas and dust burst from microscopic vents expanding outward until gravity can no longer hold them. A faint atmosphere forms around the nucleus, a glowing shroud of vapor and dust called the coma. To an observer, this looks like the comet's halo, the soft blur that hides its core. But physically, it's more like a slow-motion storm, a continual blizzard of particles streaming away from the surface, each one tracing invisible curves under the pressure of sunlight. Then from the coma, something even more beautiful and violent emerges, a tail. Not a single one, but 2 if you look closely. One is the dust tail, composed of heavier grains pushed gradually away by the sheer momentum of sunlight. The other is the ion tail, made of charged molecules carried by the solar wind, the sun's invisible storm of high-energy particles that sweeps through the solar system at hundreds of kilometers per second. Together, these tails paint the sky with light, a silent record of the sun's breath. Every particle ejected from Atlas becomes an artist's stroke, tracing the invisible wind and revealing its structure. To planetary scientists, this is not just spectacle, but data. By studying the direction and polarization of light from the coma and tail, they can read the physical properties of the dust, its size composition, even its magnetic alignment. And yet, for all the activity, the scale of violence here is difficult to imagine. Sublimation releases gas at tens of meters per second, about the speed of a hurricane from a body only a few kilometers across. Each outburst changes the comet's spin, its brightness, even its trajectory. If 3I Atlas has fractures or hollow chambers inside these eruptions, could cause sudden jets or even partial collapses, sending shards of ancient matter cascading into space. Some of those fragments, tiny as snowflakes, will continue orbiting the sun for centuries, becoming part of the faint zodiacal dust cloud that glows in Earth's night sky. But this drama unfolds beyond our sight. From Earth, the sun's glare erases the stage. Even space-based telescopes like SOHO and Solar Orbiter must look indirectly, shielding their optics behind metal discs to glimpse the faint glow just outside the star's brilliance. It is an irony. As old as astronomy, the closer something gets to the source of all illumination, the more invisible it becomes. And so scientists wait. They model the heat flow through the comet's crust, the way sunlight seeps millimeter by millimeter into its porous shell. They simulate the gas plumes, how they might drag dust and metallic atoms outward in uneven spirals. They even predict the colour of the coma pale green, perhaps from cyanide and diatomic carbon fluorescing under ultraviolet light. We know this much as 3 Atlas crosses its perihelion. It is not dying, but briefly alive, glowing, venting, transforming. Its coma is its weather system, its tail its shadow in the wind. For a few weeks the frozen silence of interstellar space will give way to light and motion. Then slowly the sun will release its hold. The heat will fade, the gases will freeze again, and Atlas will begin its long outbound journey, shrinking back into darkness, carrying new scars from its brief encounter with our star. Somewhere inside that radiant fog under layers of ice and dust, older than the Earth, there may still be a core untouched by any sunlight, a memory of another star's beginning. And as the object turns away, retreating toward the cold, it carries with it the story of its own awakening, a solar crossing written in vapor, silence, and light. The comet's fog and the solar wind. A comet is not just a rock flying through space. It is a living system, a fragile, breathing world where sunlight writes its story across a billion grains of dust. As 3 Atlas passes its perihelion, this small body, only a few kilometers wide, transforms into a vast luminous structure spanning tens of thousands of kilometers. What begins as a single point of reflected light becomes a miniature atmosphere, the coma, and beyond that, a pair of tails that trail into interplanetary night, like the brushstrokes of a cosmic painter. To understand how this transformation unfolds, imagine sunlight as a tide. Each photon is a wave of energy striking the nucleus, the solid heart of the comet. The surface, once locked in cryogenic silence, begins to boil off its outer layers. But because there's no air, there's no sound, no hiss of evaporation, only a slow, steady exhalation of gas into the vacuum. The coma grows like fog over a frozen lake at dawn, expanding outward until it becomes a glowing sphere of vapor and dust. Within that fog, the solar wind begins its work. This isn't wind in the way we know it on Earth. It's a storm of charged particles, mostly protons and electrons, streaming from the sun at nearly 1 million miles per hour. It's invisible, but its presence can be felt everywhere. It bends magnetic fields, shapes auroras, and sculpts the tails of comets into vast, graceful arcs. There are, in fact, 2 main tails, each governed by its own kind of physics. The first is the dust tail, made of microscopic grains of silicate and carbon-rich material blasted from the comet's surface. These particles are heavy by cosmic standards, so sunlight itself, through radiation pressure, gently pushes them outward. The dust tail curves, forming a broad golden ribbon that lags behind the comet's path like the wake of a ship. When people think of a classic comet, this is what they imagine: the soft arcing trail that glows amber or white in the night sky. The second subtler structure is the ion tail, and this one obeys entirely different rules. When solar ultraviolet radiation hits molecules escaping from the nucleus carbon, monoxide, carbon dioxide, water, ammonia, it strips away electrons, turning them into ions. These charged particles are immediately swept up by the sun's magnetic field, which rides outward along the solar wind. The result is a narrow, straight electric blue tail that always points directly away from the sun regardless of the comet's motion. If the dust tail shows us where the comet has been, the ion tail shows us where the solar wind is going. And sometimes those winds shift. As solar flares burst and coronal mass ejections ripple through space, magnetic fields twist and snap. When these waves hit a comet, the ion tail can flicker, break apart, or even realign in minutes, a ghostly dance caught by telescopes millions of kilometers away. It's a reminder that even a small visitor like 3I Atlas is woven into the weather of our star. At the center of it all lies the nucleus, dark, irregular, and ancient. Cometary nuclei are among the oldest materials in existence, remnants of the protoplanetary disks that formed around stars billions of years ago. Think of them as frozen archives of cosmic history, storing the ingredients of planets before planets ever existed. Inside, there is no single uniform material. Layers of different ices are mixed with dust, organics, and trapped gases, a fragile mosaic that responds differently to sunlight. Closer to the surface, carbon dioxide CO2 and carbon monoxide CO ices are the first to react. They sublimate at relatively low temperatures, around 150 degrees Celsius. These are the early risers, the ices that can awaken even in the outer solar system far beyond Jupiter's orbit. Deeper down lies water ice, which requires more heat to break free. As Atlas approaches the sun, the heat wave slowly penetrates inward, igniting new jets that burst through old fissures, changing the shape of the coma day by day. Still deeper ices like methane CH4 and ammonia NH3 may remain dormant, waiting for the faint touch of a future star that will never come. This layered structure explains why comets evolve so dramatically as they near the sun. The outgassing pattern is never uniform. Some regions warm quickly and erupt in jets. Others remain quiet, leaving plumes that twist like geysers across a frozen landscape. If we could stand above 3 Atlas and look down, we might see arcs of vapor bursting from dark craters, particles tumbling into sunlight, and plumes curling under the invisible hand of solar magnetism. The interplay of sunlight and matter here is one of the most delicate performances in the universe. A comet's glow is not its own light, but borrowed sunlight scattered and re-emitted by dust and gas. Its beauty is literally a reflection of the star that is also tearing it apart, and yet through this destruction comes revelation. Every molecule escaping from 3I Atlas tells a story about its birth. By measuring the ratios of carbon, oxygen, and nitrogen isotopes in its coma, scientists can infer the kind of star that once warmed its native system. Was it a sun-like star, bright and stable, or a red dwarf cooler and older with planets locked in eternal twilight? The answers lie within those escaping gases, the whispers of chemistry carried on the solar wind. So when we see a comet's tail stretching across the heavens, we are not witnessing a single object, but a process, a dialogue between light and matter, motion and heat. The coma is the breath of an ancient world meeting the radiation of a young star. The tail is the record of that encounter etched across millions of kilometers. 3I Atlas is now engaged in that dialogue, a visitor learning the language of our sun, and in doing so teaching us something about the forgotten corners of the galaxy where it began. For as long as its coma glows, we are in a sense connected. Our sunlight, its atoms, one fleeting relationship stitched across the silence of interstellar space. Blindfolded by daylight, there is a strange kind of blindness that sunlight brings. Every morning on Earth it reveals everything around us. Trees, clouds, faces, seas. Yet in space that same light can hide entire worlds. As 3 Atlas approaches its perihelion, the very brightness that powers its transformation has made it vanish from our sight. The reason is simple, but profound. We are on the wrong side of the sun. From our vantage point, the comet's position is swallowed by the solar glare, a flood of photons millions of times brighter than the faint reflection of light from its icy surface. Even the most sensitive telescopes on Earth, the kind that can detect the flicker of a planet hundreds of light years away, are rendered useless by this incandescent wall of radiation. Astronomers often describe this region as the solar exclusion zone, a blinding circle around the sun where nothing dim can be observed. It's like trying to study a candle flame placed beside an exploding star. The detectors saturate scattering light across every pixel, erasing the delicate signals we need most. For weeks, 3I Atlas will be hidden here, a ghost passing behind the lamp that illuminates all things. Still, humanity has its ways of seeing in the light. Several spacecraft orbit near the sun with specialized heliophysics cameras, instruments designed not to look at the sun but just beside it. The SOHO and Stereo observatories, for example, use coronagraphs, metal discs that physically block the sun's disk so that its outer atmosphere, the corona, becomes visible. These are the same tools that reveal solar flares, coronal mass ejections, and sometimes comets themselves as they skim perilously close. For a brief window, 3I Atlas may cross their field of view. If it does, it will appear as a small streak against the glowing background of plasma, a speck of borrowed sunlight, moving across a storm of charged particles. But even these glimpses are uncertain. The brightness difference between the corona and a comet's coma can exceed 1 billion to 1. Detecting such faint motion requires both precision and luck. And luck in astronomy is another word for patience. When the object finally emerges from behind the sun in early December, telescopes across the world will awaken from Mauna Kea to La Silla, from Chilean deserts to Antarctic domes. But until then, the universe demands stillness. Observers must wait through the blinding weeks, while model simulations and quiet anticipation take the place of images. There is poetry in that waiting. The same sun that hides the comet is also shaping it, blasting its surface, sculpting its tail, rewriting its chemistry in real time. We are blind to the process, yet the blindness has purpose. The object is performing its metamorphosis in private, like a chrysalis under impossible heat. When it reappears, it will no longer be the same. In the meantime, scientists work by inference tracing invisible paths through data. They calculate where 3 Atlas should be, how sunlight must be striking its surface, how the solar wind might be bending its tails. It is an act of faith wrapped in mathematics. The same equations that once guided Voyager beyond Neptune now help track this nameless speck behind the star that defines our existence. The irony is cosmic. Our sun, the source of all vision, forces us into darkness when something precious passes near it. This isn't a new frustration. In the 17th century, early astronomers had to wait for Mercury's transits, or for solar eclipses to glimpse what lay close to the solar edge. Even now, with instruments orbiting far from Earth, the same rule applies. The light that makes seeing possible also sets the limits of what can be seen. There's a quiet metaphor in that one scientists have learned to live with. Discovery in space often arrives in intervals of blindness. The universe reveals itself slowly in alternating patterns of knowing and not knowing. Between the moments of illumination, there is always a pause, a necessary dark in which we learn to interpret what light cannot tell us. So, for now, 3i Atlas belongs to that unseen realm. Hidden behind daylight, it is being remade by fire. Its crust is boiling, its tail is changing shape, its gases are writing equations into sunlight that we will decode only after it re-emerges. The data we collect later will be like reading a traveller's diary after their journey is done, the words intact, but the experience long over. Patience is the quiet engine of astronomy. It's the willingness to wait years, even decades for a return, a transit, a signal from the far side of the sun. When 3T Atlas reappears, it will carry with it the memory of that crossing of heat, of light, of being hidden and revealed. Until then, the astronomers wait their cameras idle, their calculations looping their faith unbroken. The comet is there invisible yet real, moving through the heart of radiance. And somewhere deep within that brightness, a stranger from another star continues its long, wordless conversation with our own. How we found it, Atlas. Survey night. It began, as great discoveries often do, with something routine, a faint streak of light that shouldn't have been there. On the night of July 1st, 2025, a network of automated telescopes scattered across the globe in Hawaii, Chile and South Africa was quietly performing its nightly ritual. This system, known as ATLAS, short for the Asteroid Terrestrial Impact Last Alert System, was never designed to find interstellar mysteries. Its job is humbler, though no less vital, to guard our planet. Each night, ATLAS scans the sky for objects that move. Its wide-field telescopes don't look for beauty, they look for motion. Small, silent shifts in the heavens that could someday spell danger. Every few seconds, its cameras take deep exposures, then compare them against previous images to detect anything that changes position. Most of what it finds are harmless known asteroid satellites, even the occasional bird or airplane crossing the frame. That July night began like any other. The software flagged a faint moving point of light. Its coordinates were logged, its motion vector recorded, and the system tagged it for human verification, a standard step in the nightly flow of hundreds of detections. At first glance, nothing about it stood out. Another asteroid the analysts thought probably orbiting somewhere between Jupiter and Mars. They named it, provisionally filed the report and moved on. But Atlas doesn't just look once. The Sky Patrol repeats its sweeps every few hours, scanning overlapping fields, stitching together patterns invisible in a single frame. When the object reappeared later that night, its position had shifted more than expected. By dawn, analysts were already puzzling over the numbers. The displacement was too large. The team double-checked everything: telescope calibration, image timestamps, possible tracking errors, even false positives caused by cosmic rays striking the sensor. The algorithms that underpin Atlas are built to be skeptical. They ignore spurious points, filter out reflections, and verify movement across multiple instruments. And yet, after hours of cross-referencing data from all three hemispheres, the pattern remained. The object wasn't just moving, it was racing. Within 24 hours, the calculations arrived 58 kilometers per second, the highest velocity ever recorded for a small body entering the solar system. To put that into perspective, Earth travels around the Sun at 30 km/s. Mercury, the fastest planet, does about 48 km/s. This new object was moving far faster than anything bound to the Sun could sustain. It wasn't orbiting, it was passing through. That realization rippled quietly through the astronomy community. A few researchers exchanged late-night emails. Have you seen this? Could this be hyperbolic? In celestial mechanics, hyperbolic is a special word. It means the object's speed is greater than the sun's escape velocity, that it's unbound, arriving from interstellar space and destined to leave forever. Hyperbolic orbits are rare. Most bodies in the solar system trace ellipses, closed loops of varying eccentricity. Even comets that appear to come from far away, like those from the Oort cloud, remain tethered to the sun by the faintest thread of gravity. But a true interstellar object follows a hyperbola, a curve that begins and ends in the infinite, only briefly brushing against the sun before slipping away into the dark. The Atlas team verified again. No instrumental errors, no lens flares, no artificial satellites. The data was clean. A faint moving point that refused to slow down. At that point, protocol required escalation. Observatories in Arizona, the Canary Islands, and Australia were notified to conduct follow-up tracking. Within hours, confirmation arrived from multiple sites, same trajectory, same velocity, same anomaly. The object was real. The astronomical community held its breath. The name came next, not poetic, but precise. 3E Atlas. The 3I stood for Third Interstellar, following Oumuamua 1I and Borisov 2I. The Atlas part honoured the system that found it. Somewhere in a small operations room in Hawaii, as a few tired scientists stared at the data stream, realizing they had just become witnesses to something almost mythic, a traveller from another star passing through our skies. But the excitement was tempered by discipline. Interstellar detections demand extraordinary caution. False positives can arise from gravitational assists, data noise, or incomplete tracking arcs. The software that flags anomalies must distinguish genuine hyperbolic trajectories from those distorted by observation gaps. So for several weeks, astronomers quietly watched, collecting more data points. Each new observation refined the orbital model, tightening its curve, confirming its origin. By late July, the verdict was clear. There was no mathematical way this object could be native to our system. Its speed and approach angle didn't match anything gravitationally bound to the sun. 3I Atlas had come from the depths of interstellar space, drifting for millions, perhaps billions of years before this fleeting intersection. Behind the scenes, scientists worked like detectives, reconstructing a crime scene, measuring light curves, mapping orbital vectors, comparing it to previous interstellar visitors. It was a small miracle that Atlas had even caught it at all. Most interstellar objects pass unnoticed, too dim or too distant for our instruments. That night, the timing, the sky position, and the sensitivity of the survey had all aligned, a cosmic coincidence that might never repeat in our lifetimes. Think about it, a handful of pixels on a digital sensor, no larger than a grain of sand, carrying the story of another solar system. It could have been a forgotten rock, a relic of a distant world, torn apart by its star, a frozen survivor of some ancient planetary collision. And for one brief night, its light travelled across the universe, struck a telescope mirror, and told us, "You are not alone in your debris." Discovery at its core is often just that attention-meeting chance. Atlas was built to look for threats. Instead, it found a messenger, a small object moving too fast to stay, reminding us that even the quietest nights can reveal the motion of eternity. Speed that breaks belonging. In space, speed is not just motion, it is identity. Every object that orbits our sun moves according to an ancient contract, an invisible balance between gravity and inertia. The faster something moves, the farther it can climb from the sun's grasp. The slower it goes, the deeper it falls toward the center. Every world, every moon, every grain of dust knows this law instinctively. They belong to the sun because they move just fast enough to fall forever without escaping. But 3I Atlas broke that rule. It was moving too fast for belonging. To understand what that means, picture the solar system not as a flat map, but as a gravitational well, a kind of three-dimensional bowl with the sun sitting at its base. The planets are marbles rolling around the bowl's curved interior. The deeper the marble, the faster it must move to stay in orbit. Earth rolls in its groove at roughly 30 kilometers per second, fast enough to circle the sun once every 365 days without tumbling inward. Mercury, much closer to the center, races around at 48 kilometers per second, its short orbit lasting only 88 days. Each planet's speed is a measure of how steeply it sits in the well. Now imagine throwing a pebble up from the bowl's side. If it's too slow, it rolls back down. If it's fast enough, it rises to the rim, pauses, and slides back. That's a comet on an elongated orbit. But if you throw it faster still beyond a critical threshold, the pebble never comes back. It crosses the rim and keeps going into open space. That threshold is the escape velocity, the minimum speed required to break free from the sun's gravitational pull. For the sun, at Earth's distance, that number is about 42 kilometers per second. At Jupiter's distance, roughly 5 astronomical units out, it drops to around 18 kilometers per second, because gravity weakens with distance. Most asteroids and comets out there move well below that limit content to circle the sun in their long looping paths. But when Atlas was first spotted near Jupiter's orbit, it was already racing inward at 58 kilometers per second, more than triple the local escape velocity. Nothing born of our sun should move that fast in that region. It was as if a marble had come shooting into the bowl from outside, skipping past all the rest before climbing out again. The only explanation, it was not one of ours. This is what astronomers mean when they say 3i Atlas follows a hyperbolic trajectory. The word sounds abstract, but it simply describes the shape of an open curve, a path that approaches the sun, bends slightly under its gravity, and then swings away never to return. Most objects in our solar system trace ellipses, closed loops that repeat endlessly. But a hyperbola has no closure, no repetition, no home orbit. It is the geometry of departure. If you could draw it on a graph, you'd see energy as the vertical axis and distance from the sun as the horizontal one. Every planet, every asteroid sits below the line of zero energy trapped bound. The deeper below the line, the more securely it belongs. To cross that line into the positive to enter the realm of escape, an object must carry more kinetic energy than gravity can reclaim. That is the space of the unbound, the realm of the interstellar. 3i Atlas exists above that threshold. Its total energy, the sum of its motion and its distance is positive, meaning it owes the sun nothing. No future return, no orbit, no membership in this celestial family. It will curve once through our sky and then continue outward, forever tracing an endless arc through the Milky Way. To grasp the enormity of that freedom, consider how rare it is. Every rock, every planet, every comet we have ever known, trillions of them are gravitationally tethered. Even those that drift far beyond Pluto are still faintly chained to the sun's pull, destined to fall back someday. But Atlas is different. It moves with the liberty of a wanderer between stars. Its velocity is its passport proof of origin beyond the frontier. At 58 kilometers per second, each heartbeat carries it farther than the entire Earth's diameter. In a single minute, it could cross the distance from New York to Tokyo 10 times over. Over the course of one day, it travels more than 5 million kilometers, enough to outrun every familiar rhythm of motion in our planetary system. And yet, paradoxically, this very speed makes it ephemeral. The faster it goes, the less time we have to know it. From discovery to disappearance, Atlas will spend barely half a year in our view, a brief shimmer of movement against the background of eternity. Like a meteor that never burns, it crosses our sky in silence, too distant to hear, too swift to hold. For astronomers, the speed of 3i Atlas is both triumph and torment. It confirms its interstellar nature beyond doubt, but it also ensures that by the time we fully understand it, it will already be gone. Still, that brief visit is enough to change how we think about motion itself. For every world bound by gravity, there exists another that is free. And sometimes those two realms, the bound and the unbound, meet just long enough for us to glimpse what it means to escape. In the end, Atlas reminds us that the solar system's borders are not walls, only gradients. Gravity holds most things, but not all. A little more speed, a little more energy, and the rules of belonging collapse. The sun, mighty as it is, cannot keep everything. Some travelers simply pass through, carrying with them the cold ancient memory of other stars, and the promise that the universe is more connected than we ever imagined. The third of its kind. When 3i Atlas appeared on our screens that July night, it didn't just add a new object to the catalogue of the cosmos, it joined a lineage small but extraordinary. It became only the third interstellar visitor ever observed passing through our solar system. The third time the universe has sent us a messenger from beyond the sun's domain. Before Atlas came two others, 1i Oumuamua and 2i Borisov, each as strange, each rewriting our understanding of what normal means. The first Oumuamua arrived in October 2017 like a spark from nowhere. It was discovered by astronomer Robert Weryk using the Pan-STARRS telescope in Hawaii, and almost immediately it refused to behave. It showed no coma, no tail, no gas release, yet it accelerated slightly as it left the inner solar system, as if pushed by something unseen. Its shape inferred from the way its brightness flickered was bizarre, perhaps 10 times longer than it was wide a cigar or a flat shard tumbling end over end every 8 hours. Astronomers had never seen anything like it. Some called it a fragment of a shattered planet, others a solid hydrogen iceberg, or even a piece of a nitrogen crust blasted from a distant world. A few, including Harvard astrophysicist Avi Loeb, dared to suggest it might be artificial, the relic of a probe or a piece of alien technology, its acceleration driven by sunlight on a thin reflective surface like a sail. The debate divided the scientific community, and no answer fully satisfied everyone. But one truth remained: Oumuamua was not from here. Its hyperbolic path proved interstellar origin beyond doubt. Then, in 2019, came the second 2I Borisov discovered by amateur astronomer Gennady Borisov from a homemade telescope in Crimea. Where Oumuamua had been mysterious, Borisov was almost comforting in its normalcy. It looked and behaved like a typical comet, a bright nucleus, a gas coma, a long, elegant tail. Its spectrum revealed familiar compounds: water cyanide, carbon monoxide. Yet even in that normalcy, it was extraordinary. For the first time, humanity had a clear chemical look at matter formed around another star. Comparing the two was like comparing myths from different civilizations. Oumuamua, silent, dry and shapeless, spoke of desert worlds, perhaps broken asteroids or crustal fragments from a system long dead. Borisov, icy active and radiant, hinted at wet systems full of comets and volatile rich bodies like our own. Between them they outlined a spectrum of possibilities that not all solar systems are built alike, and that what we consider normal tails, ice's gas dust, is only normal here. Now with 3I Atlas, the picture widens further. It carries traces of both of its predecessors and yet belongs fully to neither. Like Borisov, it displays a coma and releases gas, but its composition is inverted, dominated by carbon dioxide instead of water. Like Oumuamua, it carries odd optical signatures, extreme negative polarization, strange brightness fluctuations, and an orbit that enters our system in near-perfect alignment with the planetary plane, as though following the grooves of the solar disk. If Oumuamua was the whisper of something strange and Borisov the reassurance of something familiar, then Atlas is the bridge, the ambiguous middle ground that tells us there is no single pattern to the galaxy's creations. Each visitor forces us to redefine what a comet or even a planet can be. Until 2017, we assumed our solar system's blueprint, a bright star, icy comets, rocky. Worlds, gas giants, was typical. Oumuamua shattered that illusion. Borisov humbled us further, showing that familiar chemistry could thrive beyond our star's light. And now Atlas complicates the story yet again, combining familiarity and anomaly in equal measure. The diversity among these three travelers suggests that planetary systems elsewhere are as varied as snowflakes, each forming under unique conditions of temperature, radiation, and chemistry. Some may produce comets rich in carbon monoxide, others in water, others in metals or silicates we can only guess at. And as these worlds collide, fragment and scatter over billions of years, their debris drifts into the void, the raw material for interstellar visitors like Atlas. We are only now beginning to glimpse that cosmic diaspora. Interstellar objects are not just curiosities, they are samples, pieces of alien geology delivered to our doorstep. For decades, scientists dreamed of sending spacecraft to other stars to collect fragments of their planets. Now the universe has turned the equation around. The fragments are coming to us. It is a humbling reminder that our solar system is not an island but a crossroads, a place occasionally brushed by travelers carrying the mineral fingerprints of other suns. Each time one passes through, we are offered a lesson not just in astronomy, but in humility. When Atlas entered our system, it carried more than dust and ice. It carried a question: what does normal mean when the universe keeps surprising us? Every time we think we've drawn the boundary of the possible, another stranger crosses it. And if 3 visitors have arrived within less than a decade after billions of years of silence, we must wonder, have they always been coming simply unseen? Or are our eyes only now opening wide enough to notice the truth may lie in both directions? The instruments have changed, more sensitive, more vigilant. The skies are watched like never before. Perhaps interstellar travelers have always drifted through our system, leaving faint trails lost to the noise of old detectors. Or perhaps in a galaxy stirred by time and gravity, fragments from distant worlds are becoming more common, the universe scattering its stories freely into the void. 3I Atlas then is not just the third of its kind. It is the third reminder that the cosmos resists our categories. Each arrival is both answer and riddle, light and silence. And somewhere beyond the reach of telescopes, countless more may already be on their way, unseen yet inevitable, bearing the quiet signatures of other homes. Bigger, faster, stranger from the beginning. 3. Atlas distinguished itself not merely as another interstellar wanderer, but as something larger, quicker and more precise in its aim than any visitor we've ever recorded. Its differences are not subtle. They define a new category of traveller, forcing astronomers to rethink what an interstellar comet can be. Let's start with size. Where Oumuamua stretched at most 400 meters across, small enough to fit inside New York's Central Park, and Borisov measured about 1 kilometer in diameter, 3I Atlas could be 5 to 6 kilometers wide. That's enormous for an interstellar object. Imagine the city of Los Angeles frozen into a single chunk of rock and ice, then hurled across the galaxy. The implications are staggering. Size changes everything: gravity, heat retention, and how sunlight interacts with its surface. A larger comet retains heat differently. When solar radiation strikes it, the energy doesn't just skim the surface, it sinks into deeper layers, awakening gases that smaller bodies might never release. Its internal structure becomes a complex network of thermal gradients, with frozen ices buried kilometers deep. Sublimation, the direct transition from solid to gas, proceeds like a slow heartbeat, rather than a sudden burst. Each region of the surface may respond differently, creating localized jets that vent at varying times and intensities. This uneven release of gas is what gives the comet its character. It determines the brightness we see from Earth, the shape of the coma, and the strength of the tail. In 3 Atlas, that coma is massive, a fog of vaporized carbon dioxide and dust that could extend for tens of thousands of kilometers, like a drifting planetary halo. The bigger the nucleus, the more material it can shed, and the longer it can remain active, even as it travels away from the Sun. But with greater mass also comes stability. Smaller comets often fragment near perihelion, torn apart by the uneven pressure of outgassing or by gravitational stress. Borisov, though robust, eventually disintegrated under the heat. 3I Atlas, however, has shown no sign of such collapse. Its mass gives it cohesion. Its own gravity binds the escaping dust into smoother streams, and its shape, though irregular, holds together under forces that would rip a smaller body apart. Next, consider velocity. Atlas travels at nearly 58 kilometers per second, relative to the Sun almost twice the speed of Oumuamua or Borisov. That speed is not just a number, it's a signature of origin. A comet ejected from a young energetic star system can carry a slingshot boost from planetary encounters, catapulting it into the galaxy at extraordinary velocity. Over millions of years, gravity from other stars may alter its path, but not slow it much. By the time it enters our solar system, it retains the kinetic echo of its birthplace, the fossil memory of another sun. That speed also means it interacts differently with solar radiation. For instance, the faster a comet moves, the less time sunlight has to heat any single region. Its surface experiences a kind of thermal lag. The sunlight strikes, but the surface doesn't have long to respond before the object rotates and races onward. This produces uneven heating, day and night cycles that last mere hours, and it's one reason the coma of 3I Atlas flares irregularly. Some jets may ignite and extinguish within a single rotation, making the comet's brightness flicker unpredictably. For observers, this is both fascinating and frustrating. Borisov moved slowly enough that telescopes could track and study it for months in steady conditions. Atlas, by contrast, tears through the sky so quickly that even minute long exposures can blur its light. Capturing detail requires coordination observatories across continents sharing time zones, like a relay team passing the baton of observation from one night sky to another as Earth rotates beneath. Finally, the approach geometry, perhaps the strangest distinction of all. Oumuamua and Borisov both arrive from the north, plunging downward into the solar system, from directions roughly aligned with the Sun's galactic motion. That made sense. As our solar system moves through the Milky Way, we expect most interstellar debris to approach head-on like raindrops hitting a moving car windshield. But 3 Atlas defies that expectation. It doesn't come from above or below. Instead, it arrives from the side, nearly in the same plane as the planets, the ecliptic, that thin disk where Earth, Mars and the others trace their paths around the Sun. Its orbital inclination is just 3 degrees, an almost perfect alignment. In the vastness of three-dimensional space, that's an uncanny coincidence, as if a traveller crossing a city by chance happened to enter through the exact street where all the traffic flows. How improbable is that very out of all possible directions hitting this narrow plane within a few degrees is statistically rare. Some astronomers suspect it's not mere coincidence, but selection bias. We are more likely to detect interstellar objects that pass near the ecliptic because our telescopes spend most of their time looking where the planets are. Others see in it a hint of cosmic choreography, a reminder that what feels random can still echo a hidden pattern. Whatever the cause, this geometry grants us a gift visibility. Because Atlas moves along nearly the same plane as Earth's orbit, we get extended periods of observation before and after perihelion, longer arcs of motion across our sky, more opportunities to study its evolution. The ecliptic is our shared stage, and for a few fleeting months, Atlas performs upon it. Taken together, its size, its speed, its path. These qualities make Three's Atlas not just another comet, but an event. It is a natural laboratory drifting through our solar system, revealing how interstellar chemistry behaves under the touch of our Sun. Its massive body radiates more material, its high speed reshapes its reactions, its low inclination lets us watch closely. Bigger, faster, stranger, but above all, illuminating. Each of these differences widens our sense of what's possible. They remind us that the universe is not standardized, that comet is merely a human word stretched across infinite variety. 3i Atlas doesn't just visit us, it redefines what visiting means. It shows us that beyond the thin shell of our solar system lies a galaxy full of objects that follow their own physics, their own histories, their own rhythm of light and loss. And as it races along that rhythm, now carving its path through the sunlight, it carries within it a quiet truth in the language of the cosmos. Different is not an exception, it's the rule. The T-bone arrival. If you could see the solar system from far above, truly above, looking down from the galactic ceiling, you would notice something surprising. It isn't a sphere at all, but a disk, thin and elegant, like a vinyl record floating in black space. Every planet from Mercury to Neptune moves in this flattened plane orbiting the Sun, along slightly tilted tracks that rarely stray more than a few degrees from one another. Even the dust asteroids and comets that make up our celestial neighborhood tend to stay close to this invisible sheet known as the plane of the ecliptic. This shape is no accident. It is a fossil of origin. Billions of years ago, when the Sun was young and surrounded by a swirling cloud of gas and dust, the cloud began to spin slowly, then faster. As it spun, it flattened the way pizza dough spreads out under a chef's hands. Most of the material collapsed into that disk, where it coalesced into planets, moons, and asteroids. That flatness became the geometry of our existence. From above, this disk of motion might appear orderly, all the marbles rolling in the same direction, confined to the same plane. But space itself is three-dimensional, and the rest of the galaxy pays no attention to our sense of order. When we imagine interstellar visitors entering our system, we expect them to come from random directions, above, below, diagonally, the celestial equivalent of traffic from every possible lane. Statistically, that makes sense. There's no reason to expect an object wandering the Milky Way to approach us in near-perfect alignment with our own planetary plane. And yet, 3i Atlas did exactly that. Its inclination, the angle between its orbit and the ecliptic, is only about 3 degrees. In astronomical terms, that's almost flat. To put it another way, if the solar system were a table, Atlas would have slid across it like a puck on ice, barely lifting above or dipping below the surface. This alignment is so precise that astronomers quickly began calling it the T-bone approach. Imagine a car speeding across an intersection from the side, perfectly perpendicular to the flow of traffic. It doesn't follow the main direction, nor does it collide head-on. It slices across the system, laterally threading the orbits of the planets with uncanny accuracy. How unlikely is such precision in theory? Extremely. Out of all the directions available in three-dimensional space, only a thin slice about 5 degrees wide corresponds to the ecliptic's narrow zone. The chance of an interstellar object aligning within that band purely by accident is minuscule. And yet here we are, watching one glide through that corridor like it was aiming for it all along. Some astronomers view this as pure coincidence, others as a product of selection bias. The truth is, our telescopes spend most of their time looking along the ecliptic, where the planets, asteroids, and near-Earth objects live. We are quite literally biased toward our own plane of motion. It's where our instruments are most sensitive, where survey coverage is densest, and where software is tuned to detect moving points of light. So when an interstellar object happens to pass through that zone, we're far more likely to notice it than one arriving from a high angle over the poles of the solar system. In other words, Atlas may not be unusual in reality, only unusually visible. There could be hundreds of other interstellar objects slicing through the system on steep, unseen trajectories, their faint signals lost in the noise of background stars. 3 Atlas just happens to be crossing the one path where we were already looking. It's as though the universe sent countless messengers, but we only heard the ones speaking our language. Still, even with that pragmatic explanation, the alignment feels poetic, almost choreographed. There's something mesmerizing about an object born around another star gliding into perfect formation, with our own planetary disk obeying. For a brief moment, the same geometric rhythm that governs Earth, Mars, and Jupiter. That rhythm, the shared plane, is one of the solar system's defining harmonies. It dictates eclipses, conjunctions, and alignments that shape our calendars and myths. Ancient astronomers traced the wandering of planets along this same narrow path across the sky, calling it the zodiac. To them, the ecliptic wasn't just a plane of motion, it was a stage, a cosmic highway, where the gods themselves travelled. And now, across that ancient road comes a traveller from another world. For scientists, the T-bone arrival carries practical consequences too. Because Atlas moves almost exactly along the ecliptic, it passes through regions of space already mapped in exquisite detail. We can compare its position and brightness against dense catalogues of background stars, refining its orbit to unprecedented precision. The low inclination also means the comet remains visible to multiple observatories across Earth's latitudes, maximizing our observational coverage. But the same geometry that helps us also tempts our intuition. When we see such alignment, our minds instinctively seek meaning intent where there may be none. Was Atlas drawn toward the Sun by chance or by some ancient perturbation in galactic tides that nudged it onto this perfect course? We may never know. But that tension between coincidence and cause is part of what makes astronomy so quietly human. Every chart of orbits is also a chart of wonder. So as Atlas threads the solar plane, slicing through the orbits of Mars and Earth like a needle through silk, it reminds us of something profound geometry can mislead as easily as it inspires. Alignment does not mean design, coincidence does not mean purpose, and yet both can awaken awe. In the end, whether this near coplanar path is accident or inevitability, it offers a moment of symmetry between the stranger and ourselves. For a brief time across 1.4 billion kilometers of shared sunlight, the visitor from another star moves in harmony with our own celestial rhythm. A fleeting chord struck between two systems that may never meet again. From the galaxy's quieter, thick disk. If you trace the orbit of 3 Atlas backward through time, through the solar system, past the heliopause, out into the slow swirl of the Milky Way, you end up facing inward toward the luminous heart of our galaxy. From that direction, across thousands of light years, this traveller began its long unbroken voyage toward us. That line of origin is not arbitrary. It points toward a region astronomers call the galactic thick disk, a layer of ancient stars and interstellar debris that hovers above and below the main spiral plane like the faint halo of an old photograph. The Milky Way from a distance resembles a vast pinwheel, a thin disk where young stars, planets and nebulae orbit tightly packed together, and a thicker, dimmer disk composed of older, slower and far more settled matter. It is from this quieter hinterland that Atlas seems to have come. To appreciate why that matters, imagine the galaxy as a living city. The thin disk is its downtown, bright, crowded and noisy. Here stars are born in furious waves of gas collapse. Massive suns live brief, explosive lives ending in supernovae that flood their neighborhoods with radiation and heavy elements. This is where most new worlds arise, including our own sun, which circles the galactic center every 230 million years in the traffic of that busy zone. The thick disk, by contrast, is the old quarter of the city, quieter, slower and stable. Its stars formed early in the Milky Way's history around 8 to 10 billion years ago, before the galaxy flattened completely. Over time, gravitational interactions puffed up that early layer into a diffuse band extending several thousand light-years above and below the galactic plane. Their stellar density drops sharply. The skies are emptier, the distances between stars stretch wider, and cosmic events unfold in slow motion. If the thin disk is a place of collisions, the thick disk is a place of memory. Supernovae are rarer here, stellar winds are gentler, the interstellar medium, the gas and dust between stars, is thinner and colder. A comet, a planetesimal or a rogue rock ejected from its home system could drift for billions of years in near-perfect stillness, untouched by radiation shock waves or close gravitational passes. To be undisturbed in that sense means surviving the galaxy's chaos intact, preserving in its chemistry the conditions of its birth. This may be what 3i Atlas represents, a fragment from a long-forgotten world, orbiting one of those ancient amber-hued stars in the thick disk, a relic that has drifted dark and frozen through eons of quiet. Its estimated age could be 7 to 8 billion years, nearly twice that of Earth. For nearly the entire lifespan of our planet, it has been wandering through darkness, crossing vast deserts of interstellar space where the nearest sun might be 10 light-years away. Quiet in cosmic terms does not mean silent. Even in those remote corridors, gravity whispers. Galactic tides stretch and compress the fabric of orbits. The faint pull of passing stars nudges paths by fractions of a degree. Over millions of years, those tiny deflections accumulate. Bit by bit, the course of Atlas bent until it intersected ours, not through violence, but through the slow arithmetic of time. The idea of quiet in the universe is often misunderstood. We imagine stillness as absence, no motion, no change. But in astronomy, quiet means long timescales. It means that what happens takes so long that we short-lived observers perceive it as still. The stars in the thick disk do move. They orbit the galactic center like everything else. But their orbits are tilted and stretched, carrying them above and below the plane in majestic slow sweeps that take hundreds of millions of years to complete. Their calm is not immobility, it's patience. In that patience, objects like 3i Atlas can endure. In the thin disk, supernovae and stellar winds would long ago have shredded such a fragile comet. In the thick disk, where the galactic radiation field is dimmer and shock waves are rare, it could drift untouched. No nearby sun to melt it, no dense molecular cloud to scatter it, no supernova blast to vaporize it. Just an eternal winter of interstellar frost. When astronomers model the motion of interstellar visitors, they sometimes run the clock backward, millions of years at a time, using stellar catalogues to identify potential encounters. For Atlas, they've traced its past 10 million years and found that it passed near 93 known stars, but never closer than 0.3 light-years, or about 63,000 astronomical units. That distance may sound small by galactic standards, but in reality it's vast, 600 times farther than Pluto's from the Sun. For an object moving that quickly, it's barely a brush. That sparse record tells us something profound. 3i, our Atlas, has spent at least the last 10 million years alone. No close flybys, no planetary systems to disturb it, no gravitational jolts, just the faint pull of the Milky Way's core slowly guiding its long fall toward the Sun. From our vantage point, it's easy to see such isolation as emptiness. But for science, it's a gift. A body preserved in the quiet of the thick disk offers a time capsule matter untouched. Since the early epochs of star formation, its ices and dust may carry isotopic ratios unseen in any solar system object frozen, fingerprints of a chemistry older than Earth's crust. So when we study Atlas, we are not merely observing a comet. We are opening a sealed archive from another age of the galaxy, one that speaks of the first generations of stars of systems that may have lived and died before our sun ever existed. And that is what astronomers mean by quiet. It's not the silence of nothingness, but the whisper of history, stretched across cosmic time, a serenity so vast that only objects like 3i Atlas can tell its story. 10 million years of loneliness. For an object like 3i Atlas, time is not measured in days or years. It is measured in orbits that never close in distances so vast that even light takes ages to cross them. When scientists speak of its history, they don't speak of centuries, they speak of millions of years. By rewinding the comet's trajectory through space, astronomers have tried to trace its path across the galaxy to understand where it might have come from before its chance intersection with our Sun. What they found is both astonishing and humbling. Over the last 10 million years, 3i Atlas has drifted through the outskirts of our spiral arm, crossing the gravitational influence of 93 stars. Yet the closest it ever came to any of them was about 0.3 light-years, roughly 63,000 astronomical units. For comparison, the comet's present distance from the Sun at perihelion is only 1.4 AU. In other words, even its nearest encounters were 60,000 times farther away than it is from our star right now. Over 10 million years of travel, it never brushed close enough to any star to be captured or deflected meaningfully. That is cosmic solitude, an existence measured in darkness, unbroken by warmth or gravity strong enough to matter. But how do we know this? How can scientists reconstruct a path through such dizzying timescales? The process begins with orbital integration, a kind of cosmic time machine built from equations. Using data from telescopes on Earth and in space, astronomers first determine the object's current position and velocity with extreme precision. Those values become the initial conditions in a mathematical model governed by Newton's laws of motion and the gravitational field of the Milky Way. Then step by step they let the simulation run backwards, subtracting the influence of known stars and galactic tides, watching where the trajectory leads. It is in essence celestial archaeology. But like all archaeology, the further back you dig, the fuzzier the picture becomes. Every orbit integration depends on inputs, the positions, masses and motions of nearby stars. Those in turn are measured by missions such as Gaia, which maps the galaxy with exquisite precision. Yet even Gaia's measurements carry small uncertainties. Over millions of years, those tiny errors multiply, ballooning into vast unknowns. After a few tens of millions of years, the simulation's predictions dissolve into statistical fog. That's why astronomers hesitate to declare a specific birthplace for 3I Atlas. They can trace its path reliably across a few million years, enough to show that it passed through quiet regions of the galactic thick disk, far from violent stellar clusters. But beyond that, the trail vanishes into probability. Somewhere out there, perhaps 8 or 9 billion years ago, the object was born around a distant star. But which star and what kind of system we may never know. Still, even with these limits, the data tells a story of profound isolation. For 10 million years, 3I Atlas has not been close enough to any gravitational body to change its course significantly. It has coasted through interstellar space like a message in a bottle on an endless invisible ocean current. The last time it felt the pull of a parent sun, the warmth of its creation, may have been before Earth's continents took their modern shape. Think about that span of time. When 3I Atlas was still hundreds of light years away, the first hominins were just beginning to stand upright on the African plains. When it crossed within 20 light years of our future solar neighborhood, mammoths still roamed across frozen tundras. By the time it approached within a single light year, humanity had only just begun to invent the telescope. And when it finally entered the planetary plane of our solar system, the same thin disk we inhabit, it had already traveled farther than any probe we've ever launched could reach in thousands of years. For all that distance and duration, 3I Atlas remained chemically unchanged. The radiation that sculpts and destroys most comets never touched it. No stellar wind, no tidal pull. Its surface remained locked in a vacuum colder than any laboratory can simulate, around 260 E, where even nitrogen freezes solid. Every molecule on its skin is a fossil, a memory of the environment it came from. This is what makes it so valuable. In a way, 3I Atlas is not merely a traveller, it is a witness. It has passed through the empty corridors between stars, through regions where gravity's voice is a whisper, and time seems to stand still. The information it carries, the ratios of its isotopes, the types of ice in its crust, will tell us how chemistry unfolded in a part of the galaxy, long untouched by stellar violence. And yet, for all our calculations, we cannot follow its history beyond that 10 million year horizon. There lies the mystery. At what moment was this fragment thrown from its home system? Was it cast out by the birth of a gas giant, flung outward, like shrapnel from a planetary collision? Or was it gently nudged free when its parent star passed near another, losing its grip forever? We can only imagine. What we know is this 3I Atlas has journeyed alone for longer than our species has existed. For 10 million years, it has seen no sunrise, no orbit, no reflection. It has drifted through the galaxy's quietest reaches, guided only by momentum and the faint pull of distant stars. And now, after a silence older than language itself, it finds us a civilization watching from one small world, eager to listen. For us, its loneliness becomes our discovery. Its wandering becomes our mirror. Because to find something that has been alone for 10 million years is to remember that even isolation in the vastness of space can lead to connection. Tess catches a drifting dot. Before the official discovery on July 1st, before Atlas even had a name, it was already being watched silently accidentally by a spacecraft that wasn't looking for comets at all. On May 7th, 2025, 2 months before the Atlas survey flagged it as a moving object, the Transiting Exoplanet Survey satellite, better known as TESS, recorded a faint shifting speck of light in its wide-field images. TESS's mission is to hunt for worlds orbiting other stars. It stares at enormous patches of sky, capturing long continuous exposures to catch the tiny dips in brightness that occur when a planet crosses its host star's face. But in the process of watching for shadows, it also records everything else that glows or moves asteroid satellites, even the occasional interstellar visitor. That's how 3i Atlas first entered human archives, not as a comet, not as a mystery, but as an unnoticed dot of light drifting across the corner of an exoplanet survey frame. Later, once astronomers realized what Atlas was, they went back through those test datasets, a process known as precovery. Precovery is the art of finding an object's past in the photographic memory of our instruments. By locating it in older images, scientists can extend the timeline of observations backward, improving the accuracy of its orbit by weeks or months. It's detective work in reverse. First, researchers identify the object's current position and motion, then predict where it should have been in earlier data. They comb through terabytes of imagery, aligning coordinates, adjusting timestamps, sometimes spotting nothing more than a faint streak just above the noise threshold. But that faint streak, when measured precisely, can shift the known trajectory by fractions of an arcsecond, enough to rewrite our understanding of its path through space. In the TESS archive, the object appeared repeatedly across a month-long sequence of exposures. It was faint nearly at the edge of detectability, but unmistakable once you knew where to look, a dim ember gliding steadily against the fixed stars. During that period, it travelled roughly 1 astronomical unit inward toward the Sun. This was where the story became interesting. TESS's data isn't just about position, it's about brightness, or what astronomers call flux. Photometry, the precise measurement of light intensity, is the heartbeat of observational astronomy. Every pixel on a CCD camera counts photons, converting them into digital numbers. By comparing an object's flux over time, scientists can see whether it's steady or changing, whether it's reflecting sunlight, glowing from heat, or erupting with gas. For a normal inert asteroid, flux increases predictably as it approaches the Sun. The closer it gets, the more sunlight it reflects, the same principle that makes the Moon brighter when it's closer to full phase. Astronomers expected 3i Atlas to brighten by perhaps a factor of 1.5 as it moved 1 AU closer to the Sun between May and June. But when they measured the data from TESS, they found something astonishing. The flux hadn't just increased by 50%, it had increased by a factor of 5. The object was flaring far brighter than geometry alone could explain. Something on its surface was awakening. That was the first clue that 3i Atlas wasn't a rock, but a comet already active long before it reached the inner solar system. Out at the orbit of Jupiter, more than 5 astronomical units from the Sun, ordinary comets remain frozen. Their ice is locked solid. But this one was already venting gas and dust, creating a faint coma that reflected sunlight back toward the spacecraft. It was alive too early. The TESS precovery images captured that early awakening in exquisite if accidental detail. Each data point, each night's sequence became a breadcrumb marking the onset of sublimation, the first whisper of vapor after perhaps billions of years in interstellar cold. By the time Atlas's ground-based telescopes picked it up 2 months later, the process was in full bloom. These kinds of archival discoveries have become a quiet revolution in astronomy. The sky is photographed so continuously now that almost every new object can be traced backward into older images. With each precovery, orbital predictions tighten. Where once we could only guess, now we can predict with confidence how and when a body entered our view. In the case of 3i Atlas, those TESS observations reduced uncertainty in its trajectory by more than an order of magnitude. The improved data revealed not only where the object was going, but also where it had come from, confirming its inbound direction from the galactic center region, the same path astronomers would later associate with the thick disk. There's something quietly poetic about that. A telescope built to search for planets around distant stars inadvertently glimpsed a fragment of another star's debris passing through our own neighborhood. The same technology designed to measure the heartbeat of alien worlds caught the pulse of a frozen traveler, a comet whose flare of brightness told us it was waking from a sleep older than Earth itself. In science, discovery often depends less on what we seek than on what we happen to notice. TESS was listening for the shadows of planets, but it found instead the light of motion, a wandering ember that would soon ignite global fascination. Without those precovery frames, we might have missed half its story. And so long before Atlas, the telescope recognized Atlas, the object a satellite orbiting Earth had already written the first entry in its chronicle, a handful of photons recorded on May 7th, drifting across a digital sky carrying within them the memory of a world no one had ever seen. Flux that grew too fast. When the first test data were finally plotted on a timeline, each observation point a heartbeat of light, the curve didn't rise gently as expected. It leapt. What should have been a modest brightening, a slow ramp-up, as the object drew closer to the sun, instead became a five-fold surge in brightness over just a few weeks. It was as though something inside the visitor had awakened, suddenly flaring to life in the cold. For astronomers, brightness isn't just appearance. It's a physical clue, a cipher for what's happening on and around a body. In this case, the brightness or flux increased far too fast to be explained by distance alone. Normally, as a rocky asteroid approaches the sun, the extra light it reflects follows simple geometry. The closer it comes, the more photons strike its surface and bounce toward us. The math is neat halve the distance to the sun, and the sunlight grows 4 times stronger, the inverse square law. But Thrush Atlas wasn't halving its distance. It moved only from about 5 to 4 astronomical units, a small change that should have yielded a modest 1.5's brightening at most. Instead, its reflected light multiplied 5 times. Something new was adding to the glow. That something was a coma, a halo of gas and dust bursting from the surface. As ices on the nucleus began to sublimate, they dragged tiny solid particles into space. Each one acted like a micro-mirror, scattering sunlight in all directions. The comet, once a single, reflective rock, suddenly became a cloud of reflectors. What had been a pinpoint became a sphere of dust tens of thousands of kilometers across, transforming its visual character almost overnight. But even that doesn't fully explain the speed of the brightening. The effect is non-linear, a kind of runaway amplification. Here's why: when a small amount of gas escapes, it lifts a little dust. That dust absorbs sunlight and warms the surface beneath, releasing even more gas, which frees more dust, which reflects more sunlight, and so on. It's a feedback loop, the cometary equivalent of an avalanche, where one unstable patch triggers a chain of activity. 3 eyes, Atlas was crossing a thermal threshold, and once it did, brightness climbed exponentially rather than steadily. The details of that process are encoded in something astronomers call the phase angle, the geometry of how light scatters between the sun, the object, and the observer. Imagine holding a ball under a lamp and looking at it from different positions. When you look straight toward the lamp, the illuminated face is bright. From the side, it dims. Comets behave the same way, but their comae amplify the effect. The microscopic dust grains scatter light preferentially at certain angles, creating bursts of reflected brightness that can change dramatically as the object's orientation shifts. During that May-June period, where Atlas's phase angle increased slightly, as seen from Earth only a few degrees, yet the resulting enhancement of reflected light may have doubled the apparent flux. Combined with the dust avalanche, the object seemed to glow far more strongly than its distance alone could justify. There's also the matter of albedo, the measure of how efficiently a surface reflects sunlight. Asteroids tend to be dark, with geometric albedos around 0.05, meaning they reflect only 5% of the sunlight that hits them. Cometary dust, especially when freshly ejected, can be much brighter, reflecting 10 to 20% of the light. Multiply that by the sudden increase in surface area from millions of tiny grains, and the total reflected light can jump by orders of magnitude. What Tess saw then was not an illusion. It was physics in motion, sunlight meeting volatility, geometry meeting chemistry. Each data point in its light curve told a piece of the story, not a static rock orbiting obediently, but a body waking into chaos caught between thermal inertia and the relentless pressure of photons. For the scientists who study photometry, the science of measuring light, this kind of outburst is both a puzzle and a gift. The shape of the light curve, the steepness of its rise and fall can reveal what the naked eye never could, how deep the heat penetrates, how fast the coma expands, even what the dust grains are made of. By modelling the flux variations, astronomers could infer that the particles were likely micron-sized silicates and carbon compounds, the kind of fine material that scatters visible light efficiently. And then there's the time factor. The flare in brightness unfolded over mere weeks, an eye blink compared to the object's million-year journey. It's as if the comet spent an eternity frozen, then in one swift gesture released its memory into light. Every photon it reflected carried a hint of its long dormancy, now transformed into motion, into spectacle. To anyone studying the data, this was the precise moment when 3I Atlas ceased being an asteroid and became a comet the moment it announced itself. It was no longer a cold, anonymous intruder. It was an active body venting its history into space. The numbers made it undeniable the flux had grown too fast, too far too bright. In a universe where most things move predictably, 3I Atlas reminded us that sometimes even in the vacuum of interstellar space, awakening can be sudden and dazzling. The light that comes back wrong when light leaves the sun, it travels outward pure and unaltered, a flood of electromagnetic waves radiating in all directions. But the moment that light touches something dust, gas, rock, ice, it changes. It scatters, reflects, bends, and in that scattering it carries back secrets about whatever it met along the way. For scientists studying comets, this scattered sunlight is a diagnostic tool as revealing as a fingerprint. They analyze not just how bright the reflected light is, but how it's polarized. And it was here in the subtle dance of light vibrations that 3I Atlas began to look profoundly alien. To understand why, let's start with a brief primer. Light can be thought of as waves oscillating in many directions. Normally the vibrations are random, tangled, unpolarized. But when light bounces off a surface or passes through dust and gas, those waves become organized. Some oscillation directions are absorbed or redirected, others enhanced, producing polarized light. In astronomy, a polarization carries geometry and chemistry in its patterns. If sunlight scatters off dust at a right angle, we get what's called positive polarization. The electric field of the light vibrates perpendicular to the scattering plane. That's the common case. Nearly all comets and asteroids show some degree of positive polarization, typically a few percent. It's what you'd expect from fine dust made of silicate or carbon compounds, the usual ingredients of cosmic debris. But if the scattered light comes back vibrating parallel to that plane, it's negative polarization, rarer, harder to explain, and often linked to special surface properties, very fine grain size, compact microstructure, or unexpected chemistry. It's a sign that light is being reflected in ways our familiar models struggle to predict. When astronomers measured the polarization of 3I Atlas, what they found was unprecedented. Its light didn't behave like that of a normal comet or asteroid. The degree of polarization was not just negative, it was extremely negative, the most extreme ever recorded for any solar system body. The photons that left Atlas seemed to twist back toward us in the wrong orientation, as if the object's surface were reshaping the rules of scattering themselves. So what could do that? The leading suspects are all microscopic: the texture and composition of the dust grains that make up the comet's coma. Imagine a cloud of particles, each no wider than a strand of smoke floating tens of thousands of kilometers around the nucleus. The way they interact with sunlight depends on their size, shape, and porosity, how full of holes they are. In our solar system, most cometary dust consists of porous aggregates, fluffy clusters of smaller subgrains bound loosely together like cosmic ash. These structures tend to scatter light strongly and produce mild positive polarization. But if the particles are denser, smoother, or coated in specific minerals or ices, the reflected light can flip its polarization direction. The data from Atlas suggests grains that are compact and fine, perhaps sub-micron in scale, with unusual composition, possibly rich in metals like nickel or in carbon-based compounds that behave differently under sunlight. Some models suggest the grains could even be glassy, formed by slow radiation exposure in deep space that melted and fused micro-ices into transparent crusts. That would make them highly reflective at certain angles, yet absorbent at others, a recipe for producing the bizarre negative signal we see. In laboratory analogues, such behavior can be mimicked by dust made of amorphous carbon-iron sulfides or heavily irradiated ices. These materials scatter light unevenly, their electrons vibrating in unpredictable patterns that confuse ordinary polarization filters. In other words, when sunlight strikes them, it comes back wrong. Why is that so important? Because polarization is one of the few ways we can read texture at a distance. We cannot land on 3I Atlas. We may never even see its nucleus clearly. But by studying how its reflected light twists, we can reconstruct the story of its surface. And that surface is nothing like the familiar crusts of solar system comets. It's darker, denser, and somehow older, a fabric woven in alien conditions. Consider what that means in cosmic context. Every planetary system bakes its dust in its own furnace of radiation and chemistry. The colors and textures of those grains are like dialects of light unique to each star's spectrum and environment. When 3I Atlas shines back polarized light that refuses to match anything in our records, it's as if it's speaking a foreign photonic language. To some scientists, this is thrilling. To others, frustrating. Polarization is tricky business. It depends not only on composition but also on viewing angle wavelength and even the internal alignment of the particles. But when an outlier like Atlas appears, it becomes a natural laboratory for testing new scattering theories, from fractal aggregate models to electromagnetic simulations that account for irregular surfaces and magnetic alignment of grains. At its core, though, the message is simple. The light we see from 3 Atlas isn't wrong, it's different. It tells us that what counts as normal in our solar system is not universal. Our comets, with their soft carbonaceous dust and gentle positive polarization, are merely one variant among countless others scattered across the Milky Way. Perhaps in another star system, comets with negative polarization are the norm, their dust shaped by different chemistry, different radiation, different beginnings. To them, our light would look strange. When you think of it that way, polarization becomes more than just a technical measurement. It becomes a metaphor for perspective, how the same light can reveal or conceal depending on where you stand. 3I Atlas sends us light that doesn't fit our expectations, reminding us that the universe doesn't owe us familiarity. In the end, the photons that bounce off its surface travel for minutes before reaching us, crossing 200 million kilometers of space. They arrive slightly twisted, subtly defiant, carrying a whisper from another world. The light is not wrong, it's simply not from here. A coma born in the cold. Something about 3I Atlas broke the rhythm of everything we thought we knew about comets. By all standard models, it should have remained inert, a dark, silent speck drifting through the outer solar system, until it crossed the warmth threshold somewhere near 3 astronomical units from the Sun. But long before that, when it was still more than 5 astronomical units away, beyond Jupiter's orbit where the sunlight is weaker than a 25-watt bulb across a football field, 3I Atlas was already alive. Telescopes picked up a faint halo surrounding the object, a delicate envelope of vapor and dust, a coma that should not have existed yet. The implication was staggering. This comet was sublimating, early awakening in a region too cold for ordinary comets to stir. To understand how unusual this is, we need to look at what drives a comet's activity. Most comets in our solar system are powered by water ice. When they approach within about 3 AU, the sun's warmth begins to seep through their crusts, raising internal temperatures above the critical point where water molecules leap straight from solid to gas. That sublimation drags dust into space, forming the familiar glowing tails that adorn our night skies. But water ice requires a lot of energy to vaporize. It has a high latent heat of sublimation, about 2,800 kilojoules per kilogram. Out in the cold beyond Jupiter, sunlight is simply too feeble to provide that energy. The result: silence until the comet ventures inward. The Atlas defied that pattern. Spectral analysis showed that its early coma wasn't dominated by water vapor at all. It was carbon dioxide, CO2, boiling away like dry ice under a heat lamp. And that makes perfect physical sense because CO2 sublimates at temperatures around 78 degrees to nearly 200 degrees warmer than the threshold for water ice. It doesn't need tropical sunshine, even the meager warmth beyond Jupiter can set it free. Picture a block of dry ice sitting on a theatre stage. It never melts into a puddle. Instead, it ghosts itself into vapor flowing like smoke that hugs the floor. That's what 3 Atlas was doing, its surface exhaling in slow motion, creating a misty aura visible across astronomical units. The faint sunlight out there acted like the glow of a distant candle, weak but relentless enough to coax CO2 molecules from the comet's crust after billions of years of dormancy. This CO2-driven activity explains not only why the coma appeared early, but also why it looked different, thin, diffuse, and strangely steady. Carbon dioxide jets produce smaller dust grains and gentler plumes than the explosive vents of water ice nearer to the sun. The result is a soft, wide halo rather than sharp, fan-shaped jets. To an observer, it might resemble the quiet breathing of a sleeper rather than a storm, but the chemistry tells an even deeper story about where 3I Atlas may have formed. In our solar system, CO2-rich comets are rare, and when they do occur, they tend to originate from the outermost regions of the protoplanetary disk beyond the so-called CO2 snowline. That's the distance from a newborn star where temperatures drop low enough for carbon dioxide to freeze solid. Inside that boundary, CO2 remains a gas and escapes into space. Beyond it, it condenses and becomes part of a planet or comet's icy body, For our Sun, that snow line lies somewhere near 10 astronomical units around the orbit of Saturn, but the ratio of CO2 to water in Atlas was nearly 8-to-1, the inverse of what we find in solar system comets. That suggests it formed in a place far colder than even Saturn's realm, perhaps near the edge of its original star's planetary system, or in a region of that star's nebula permanently shadowed and frigid. In such a nursery, water may have been too scarce to dominate. Carbon dioxide, carbon monoxide, and methane would have been the primary ices condensing into layers of frost that remained untouched for billions of years. Over time, cosmic rays and ultraviolet radiation would have hardened those layers into a crust brittle but enduring. When that comet was finally ejected into interstellar space, it carried those frozen chemistries with it, sealed in the deep cold between the stars. That is the relic now gliding through our solar system, a frozen climate record from another sun. Its early awakening is not an anomaly, but a memory, a signature of the thermal conditions in the place where it was born. To astronomers, this is priceless. It means that 3i Atlas offers a window into a planetary nursery colder and more distant than anything we've yet explored. And the physics of its behavior, how much gas it releases, how its brightness changes, let us reverse engineer that birthplace. The balance between CO2 and H2O activity tells us the temperature gradients of its parent disk. The dust composition hints at the kinds of minerals that coexisted with those ices. Every particle escaping now is a messenger from that ancient formation zone. By late summer 2025, as the object approached 4 AU, the story was already shifting. Water ice had begun to join the mix, its sublimation triggered by the stronger sunlight. The ratio of CO2 to H2O slowly flipped, marking a transition from an alien chemistry to a more familiar one. For the first time in billions of years, 3i Atlas was breathing both gases at once, half of another system, half of ours. It's difficult not to see poetry in that moment. A comet from another star awakening in a new sun's light, changing its behavior to match ours. Its coma born in the cold was learning to speak the language of warmth. And while we might analyze the process in terms of energy balances and sublimation curves, there's something quietly emotional beneath it, the recognition that even ice can remember where it came from, and that the universe's deepest stories often begin not in fire but in frost, the great gas reversal. By the time 3i Atlas reached the inner solar system, everything about it had begun to change. The quiet carbon dioxide breath that had defined its early coma was giving way to something louder, hotter, and unmistakably more familiar. Somewhere near 1.5 astronomical units from the Sun, roughly between the orbits of Mars and Earth, the comet crossed a boundary invisible but transformative. The delicate balance of gases flipped. What had once been a CO2-dominated outflow became a flood of water vapor. The numbers were startling. Observatories recorded outgassing equivalent to a fire hose blasting full force into the void, a continuous jet of water vapor streaming from vents across the surface. Within days, the production rate outpaced even that of typical solar system comets at similar distances. The ratio of carbon dioxide to water, once 8-to-1, now inverted. 3i Atlas had entered its second life. The reason for this reversal lies deep within its body, where temperature and composition perform a complex ballet. A comet's nucleus isn't uniform, it's layered like a geological onion, the result of countless freeze-thaw cycles and eons of cosmic radiation. The outermost crust is hard and desiccated, baked by earlier passages near its parent star, or by slow aging in interstellar space. Beneath that crust lie strata of volatile ices, CO2, CO, CH4, NH3, and H2O, each with its own sublimation threshold. Those thresholds are crucial. CO2 turns to gas around 78 degrees. Water ice, by contrast, requires roughly 25 degrees or warmer to vaporize in vacuum conditions. As 3i Atlas drifted inward, the sunlight intensified by the square of its proximity. What had once been a feeble trickle of heat beyond Jupiter became a blazing radiative wavefront near Mars. Slowly that energy seeped into the nucleus. At first it only warmed the upper layers, deepening the CO2 activity, but the further it fell toward the Sun, the more heat penetrated, diffusing downward, millimeter by millimeter, then centimeter by centimeter. Thermal waves in comets don't travel instantly. They migrate like tides of warmth, taking weeks to reach new depths. Somewhere inside Atlas, that migrating front encountered a buried stratum of water ice, and the effect was explosive. Unlike CO2, ice-water ice forms tougher bonds locking dust grains together in a kind of frozen cement. When it begins to sublimate, the pressure beneath the overlying crust can build dramatically. Cracks spread, vents open, sometimes entire slabs lift away in jets. It's as though the comet's mantle suddenly finds itself breathing for the first time. Astronomers call this moment mantle breakthrough. For 3i Atlas, that breakthrough happened around 1.5 AU. The sunlight, stronger by a factor of 10 compared to where it had awakened, drove the subsurface temperatures past the water ice threshold. Once a single vent opened, the process cascaded. Escaping vapor eroded its own pathways, widening cracks, liberating deeper pockets of ice. Pressure from below blew dust skyward in plumes kilometers tall, expanding the coma and increasing the reflective surface area exponentially. We can model this like a moving frontier of heat. Imagine the comet as a layered globe, each ring a different kind of ice. As sunlight warms the surface, an invisible front of thermal energy moves inward. First, it triggers CO2 near the surface, then water deeper down, then perhaps CO or other exotic ices even farther inside. The front's progress is uneven, guided by the nucleus's rotation, its shape and its shadowed hollows. Every sunrise on its spinning surface ignites a new patch, while every night lets it refreeze slightly, creating a rhythm of hissing dawns and silent dusks. In high-resolution telescopic data, this translated to subtle flickers in brightness, rapid photometric oscillations that revealed a rotation period of perhaps 8 to 10 hours. Each spin carried new regions into daylight, producing alternating surges and lulls of vapor. For planetary scientists, this wasn't just spectacle, it was a diagnostic. By tracking those fluctuations, they could map the comet's thermal inertia, how quickly it absorbed and radiated heat. What emerged was the portrait of a nucleus surprisingly dark and compact, its surface likely coated with carbonaceous material but riddled with fractures. Through those fractures, the inner ice responded to solar heat like a slow-motion geyser system. And here's the paradox: even as Atlas grew more normal, resembling the behavior of our homegrown comets, its journey there was profoundly different. Its chemistry had flipped in reverse order, awakening with carbon dioxide, then crescendoing with water. This told scientists that its volatile stratigraphy, the arrangement of ices by volatility, was inverted compared to most comets born near our Sun. Where ours formed in a warmer protoplanetary disk that layered water first and carbon dioxide deeper, Atlas likely formed in a colder environment that froze CO2 on the outside and water deeper within. So as it fell toward the Sun, the heating front worked backward through its history, melting its childhood last. By late September 2025, the new water-dominated coma had engulfed the older CO2 plume, and the comet's light curve surged once again. Its brightness grew more erratic, driven by the interplay of sunlight rotation and venting pressure. Each plume carried not only vapor, but grains of dust and trace metals, nickel, iron, magnesium that glittered faintly in ultraviolet spectra. If you were standing on its surface, then an impossible dream, you'd see jets roaring from fissures, flinging snow-like particles that curved gently in the weak gravity, falling back in slow arcs, or escaping into the coma forever. The ground beneath would tremble faintly with each outburst, and above it all the Sun, a small but dazzling star, would hang in a jet-black sky, turning this ancient fragment of another world into a fountain of light. This is the great gas reversal, the moment when one star's relic learned to breathe a new star's warmth. CO2, the ghost of its birthplace giving way to H2O, the language of ours. Its chemistry as narrative, an object telling the story of two suns through the order in which its ice is awake. Part 17. Nickel without its shadow. Even before the fire hose of water turned the comet's coma into a glowing veil, astronomers were already puzzled by something subtler, a chemical imbalance in the gas itself. Spectrographs aimed at 3i Atlas during its approach detected faint metallic emission lines shimmering through the cloud of vaporized ice. That alone was astonishing. Metals like nickel and iron don't sublimate easily. They're born in the cores of dying stars fused in the crucible of a supernova, and they typically stay locked inside solid grains for billions of years. In comets from our own solar system, both appear together in trace amounts, evaporating only when the nucleus is baked by close solar heat. But in the case of 3i Atlas, something was off. The instruments saw nickel but no iron. It was as though one twin had stepped into the spotlight while the other stayed hidden. For weeks that imbalance persisted, clear signatures of neutral nickel atoms glowing faintly in ultraviolet light while iron remained silent. Only much later, near perihelion, would iron finally appear and the nickel-to-iron ratio normalize. To scientists, that was an enigma wrapped in thermodynamics. Nickel and iron are cosmic siblings forged side by side in stellar explosions. Every known planet, asteroid and comet inherits them in roughly equal proportion because they condense together out of the same vapor of heavy elements ejected by ancient stars. The chemistry of our solar system's birth carries their fingerprints in near lockstep. So why was Atlas shedding one metal but not the other? One hypothesis begins deep inside the comet's dusty skin. Imagine its nucleus as a frozen mosaic ices, binding grains of rock and metal in complex microstructures. When solar heat triggers outgassing, it isn't just the ices that escape. The erupting carbon dioxide and water vapor can drag along embedded dust particles like a wind-lifting pollen. If those grains are coated with nickel-rich compounds or contain ultra-fine inclusions of pure nickel, they may be carried aloft more easily than heavier iron-bearing ones. The difference in density between nickel and iron is small, but in microgravity, even subtle aerodynamic effects inside the jets can separate them an atomic-scale version of a sandstorm sorting light and heavy dust. Another clue comes from the chemistry of condensation. In the young protoplanetary disks where comets form, nickel and iron condense at slightly different temperatures. Nickel tends to form stable sulfides and oxides, earlier often embedded in tiny heat-resistant grains, while iron can remain gaseous a little longer before cooling into solid form. If 3 Atlas was born in a region extremely poor in sulfur or with unusual redox conditions, that is the balance between oxidizing and reducing reactions, it might have locked nickel into shallow surface layers while burying iron deeper. Over billions of years in interstellar space, cosmic rays could have further altered those outer layers, darkening them and leaving nickel-rich residues near the surface. So when sunlight reached those crustal depths, nickel was the first to wake. Its compounds sublimated or were carried upward by escaping CO2, giving the early coma its metallic glow. Iron trapped deeper or bound into tougher silicates lagged behind. Only later, as the heating front pushed farther inward when water began to vent violently, and the crust fractured wide open, could the iron join the exodus, bringing the metallic ratio back into balance. To confirm this, scientists tracked how the emission lines changed over time. The nickel lines faded, reappeared, and shifted slightly in strength as the comet rotated and its activity zones cycled in and out of sunlight. The time-variable spectrum suggested that different regions of the nucleus had distinct compositions pockets, where chemistry froze differently during formation. In a sense, each vent was telling its own chapter of the comet's history. There's also a more exotic possibility that the nickel wasn't pure at all, but bound into organometallic compounds, complex molecules formed when carbon and metal atoms intertwine. Such molecules can survive at surprisingly low temperatures and decompose under mild heat, releasing nickel gas long before solid metallic grains would melt. If Atlas's dust formed in a carbon-rich environment, perhaps around a cool, dying star rather than a sun-like one, it might naturally carry such exotic chemistry. Whatever the mechanism, the temporary nickel without iron phase became a signature of Atlas's individuality, a quirk that spoke of its alien heritage. It reminded astronomers that even the most universal processes like the nuclear synthesis of heavy elements can manifest differently depending on the histories of the systems that inherit them. In a more human sense, the episode was strangely poetic. For weeks, the comet's spectrum resembled a solo performance, one metal singing alone in the dark, its spectral lines faint but distinct. A reminder that every element in the periodic table carries a story of fire and collapse of stars that died so matter could live again. When iron finally joined the chorus, the harmony returned and Atlas began to sound more familiar, but by then the message was clear. What we think of as normal is just what happens here in this solar system. Elsewhere, the same ingredients might play to a different rhythm. Nickel without its shadow was a glimpse of that other rhythm, the quiet dissonance of a material born under another sun. And as we watched the metals dance in and out of its coma, changing week by week, we realized we weren't just studying a comet. We were watching a living chemistry experiment billions of years old unfold one element at a time under the touch of our star. Part 18. The tail that pointed the wrong way. For all its strangeness, its alien chemistry, its early awakening, its impossible polarization, the most startling image of 3i Atlas may be the one that first seemed like a mistake, a comet with its tail pointing toward the sun. In the language of cometary physics that's nearly sacrilege, tails, after all, are supposed to trail away from the sun, not reach toward it. They form because solar radiation and the charged particles of the solar wind push dust and gas backward, sweeping them into the long, luminous streamers we see in photographs. It's so fundamental that comet tail, just opposite the sun, is among the first facts any student learns about the sky. And yet when astronomers first imaged 3I Atlas in mid-2025, the faint thread of dust streaming from its coma didn't follow the rule. It leaned sunward, a ghostly fan facing the very star that should have been pushing it away. At first there was confusion. Was it an illusion, an error in image processing, or perhaps a misalignment in the telescope's orientation? But subsequent observations confirmed it. The tail really did appear to bend toward the sun. For a time, 3I Atlas seemed to defy the physics that shaped every other comet we knew. The explanation, as it turned out, was a perfect storm of geometry, timing, and environment. Projection and perspective play the first trick. A comet's tail is a three-dimensional structure tens of millions of kilometers long, curving gently under the influence of solar radiation and the comet's own motion. From our vantage point on Earth, we see only its two-dimensional projection on the sky. If the comet's orbital path happens to line up with our line of sight, the tail can appear to angle forward, even though in space it's still trailing behind. It's the same optical illusion that makes airplane contrails sometimes seem to point ahead of the jet when viewed from below. But geometry alone didn't explain everything, because the measured scattering angles of sunlight off the dust grains were inconsistent with a purely backward tilted tail. The pattern of brightness along the plume suggested something more. The grains themselves were not behaving as expected. In the early months of 3I Atlas's activity, the solar wind was weak. The sun was still climbing toward its cycle 25 maximum, but the magnetic field orientation at that time was tangled and inconsistent. The charged particles streaming outward, electrons and protons traveling at hundreds of kilometers per second, were not strong enough to sweep away the heavier dust grains that Atlas was shedding. Those particles, millimeters in size, were ejected gently by CO2 sublimation at only a few meters per second, and their inertia kept them orbiting roughly along the comet's trajectory instead of being blown backward. So while the finer, lighter grains began to drift slowly, anti-solar, the larger grains lingered near the sunward side, creating what's known as an anti-tail, a feature that from our perspective seems to point toward the sun. It's a trick of motion and timing. Old dust moving on curved orbits intersects our line of sight just right, forming what looks like a backward tail, even though it's actually a thin sheet of particles lying within the comet's orbital plane. Anti-tails are rare but not unique. History has seen a few famous examples. Comet Arend-Roland in 1957 astonished astronomers by growing a bright sword-like ray aimed directly at the sun. For days it looked like the laws of physics had inverted, until careful calculation showed it was simply a projection of dust from a previous outburst that Earth happened to pass through. Comet Hale-Bopp in 1997 displayed a similar phenomenon, a stubby sunward spike appearing just before perihelion, caused by large grains released months earlier that had drifted into a thin dust sheet. 3I Atlas joined that short elite list of optical tricksters. Its early CO2-driven activity likely expelled coarse, nickel-stained grains that were too heavy for the feeble solar wind beyond Mars to move efficiently. When viewed from Earth, those slow-moving grains still near the orbital plane caught sunlight and created the illusion of a sunward-facing fan. Then, as the comet drew closer and the solar wind strengthened, reality reasserted itself. The fine dust produced by the water ice jets, lighter, more reflective, more responsive to radiation pressure, began to dominate the coma. The true anti-solar tail emerged, sweeping gracefully away from the sun in the familiar fan shape. By September, that tail stretched for hundreds of thousands of kilometers, a faint golden streamer marking the comet's flight path across the planetary plane. The earlier anti-tail faded, dissolving into the background as larger grains fell behind or dispersed. This brief inversion was more than just a curiosity. It was a diagnostic of dust physics in motion. It told scientists about the size distribution of grains, the speed of their ejection, and the relative strength of the solar wind at that distance. By modelling the changing tail geometry, astronomers could infer the mass loss rate of the comet and the drag forces acting on individual particles, a natural experiment in microgravity aerodynamics. But beyond the technical data, there's something poetic in that image of a comet with a tail that points the wrong way. It captures the essence of astronomy itself, the tension between what we expect to see and what the universe decides to show. Sometimes light deceives us not to confuse, but to teach, to remind us that perspective is part of every truth. For a few brief weeks, Thirussia Atlas seemed to move against the solar wind, a traveller resisting the push of the star that had awakened it. But in the end, physics prevailed, and its tail turned gracefully back, joining the ancient choreography of dust and light. Still, that moment of reversal remains etched in its story, a fleeting portrait of disobedience, reminding us that even comets, those patient archivists of the cosmos, can have moods. A Martian window opens on October 3rd, 2025. The red planet turned into a cosmic observatory. For a brief moment, Mars stood in the perfect position, the closest of all the worlds to 3i Atlas, just 0.19 astronomical units away, about 28 million kilometers. For interplanetary standards, that's almost intimate. From that vantage, humanity had cameras, waiting robotic eyes already perched on and around the Martian world. Here, distance and destiny aligned. While Earth's view of Atlas was blocked by the sun's glare, Mars had a clear night sky. And so, on that date, our first true photographs of the interstellar traveller came not from home, but from another planet. The most haunting of those images came from the Perseverance rover sitting quietly in Jezero crater. Its main job is geology, not astronomy, but its cameras are sensitive enough to catch the faint trails of meteors and moons. Engineers commanded it to take a series of 30-second exposures one after another as the comet glided across the thin Martian sky. Individually, those frames showed almost nothing, just specks and static. But when scientists stacked the images, aligning them on the predicted path of the object, a single thin streak of light appeared through Atlas, captured from another world. The picture isn't much to look at. No grand tail, no glowing halo, just a silver thread through darkness. But its meaning is immense. It marks the first time in history that a non-terrestrial camera has photographed an interstellar object. The light in that image travelled from another star, touched the comet, and then reflected off a Martian lens, a chain of cosmic relays stretching across worlds. Orbiting above the ExoMars Trace gas orbiter, operated jointly by the European Space Agency and Roscosmos, also caught sight of it. Using its onboard cameras, scientists imaged a faint blur against the star field, the coma unresolved but distinctly brighter than the background. From orbit, Mars offered a stable, vibration-free platform, and those data confirmed what the Perseverance image only hinted: the comet's brightness and morphology were consistent with a wide, dust-rich coma about 100,000 kilometers across. To many, these were more than photographs. They were proof of cooperation across planets. For once, our fleet of robots scattered through the solar system acted as a single observatory, a network that turned Mars, Earth, and space itself into a triangulated sensor. The result: new precision in measuring Atlas's orbit and behavior. By comparing the comet's position relative to background stars as seen from Mars and Earth-based telescopes, when Earth finally regained visibility months later, astronomers could refine its distance and motion far beyond what a single perspective allows. This technique, called astrometric parallax, is as old as astronomy itself, but here it unfolded across an interplanetary baseline. Two worlds became the endpoints of a measuring stick stretching nearly 1.5 astronomical units wide. From that separation, even a shift of a few pixels between images revealed the comet's true trajectory with exquisite clarity. And yet the view from Mars remained limited. Neither Perseverance nor ExoMars was designed for deep space imaging. Their optics, optimized for landscapes and atmospheric studies, could not resolve fine detail in the nucleus or the inner coma. For that, scientists looked hopefully to the Mars Reconnaissance Orbiter home, to the HiRISE camera, one of the most powerful telescopes ever sent beyond Earth. HiRISE has a resolution so sharp it can read the tread marks of a rover's wheels from orbit. If aimed correctly, it could have captured 3i Atlas as a condensed structured object, perhaps even distinguishing the brightness of its coma from the nucleus beneath. But timing worked against us. Around that same period, a partial government shutdown in the United States suspended non-essential NASA operations, leaving many teams unable to upload new commands. The result: the potential HiRISE observation remains uncertain, perhaps never taken, perhaps still waiting in raw data archives to be processed. Even so, the symbolism of those Martian observations is unforgettable. On a world that humans have never set foot upon, our mechanical emissaries lifted their eyes to watch an interstellar wanderer pass by. The dust on their solar panels had once been Martian. The photons they caught were from another star system entirely. It was a quiet meeting of worlds, one dead, one alive, and one ancient visitor that had crossed between them. These images also underscored the growing importance of multi-world astronomy. Until recently, all of humanity's telescopes shared one vantage point Earth. Now our reach spans to the Moon, Mars, and beyond. When we observe from multiple locations, we gain not only sharper geometry, but new insight into the scattering of light, how comets and tails appear under different solar angles. From Mars, the sun's illumination came from a different side, allowing researchers to model the comet's density distribution and the particle size of its dust. Each observation refined our understanding the comet's brightness, asymmetry, its gas emission spectrum, its faint reddish hue, hinting at iron-bearing grains mixed with carbon-rich dust. The Martian data, though sparse, became a crucial piece in a puzzle too large for one planet to solve. It's easy to imagine a future when such interplanetary collaborations become routine, when rovers on Mars, probes around Jupiter, and telescopes on Earth coordinate to observe the same target, creating a solar system-wide observatory. Atlas gave us a taste of that possibility. When we look at the Perseverance image now, that fragile streak scratched across a Martian night, we're reminded that, even in a world without life, human curiosity finds a way to see. The dust of Jezero crater has never known water in billions of years, yet it bore witness to a traveler carrying frozen water from another sun. From that lonely red world, we caught our first glimpse of an interstellar comet up close. And though the picture was faint, it whispered something extraordinary, that the universe is vast enough to connect worlds not by roads or rockets, but by shared light. Waiting through the solar blind. As October faded into November, Atlas disappeared into the very glare that gives life to everything we see. The sun, that cosmic searchlight, had become its curtain. For all of our telescopes, cameras, and spacecraft, the visitor was now invisible, a ghost hidden in daylight. This was the solar blind, the unavoidable intermission in every inner solar system drama. Once a comet sweeps too close to the sun, as seen from Earth, the star's brilliance drowns all other light. Even our most advanced ground-based instruments, from the European Southern Observatory to Mauna Kea, must avert their gaze. It isn't a matter of power, it's geometry. The comet's angular distance from the sun, or solar elongation, had shrunk below 10 degrees, putting it squarely in the glare zone where detectors saturate and mirrors risk damage. And so, for the first time since its discovery, astronomers had to stop looking. It's a strange feeling, this forced stillness. After months of watching a new world unfold each week, bringing fresh spectralite curves and puzzles, the sudden pause feels almost like separation anxiety. But this waiting period isn't wasted. It's a time of preparation and quiet collaboration, a moment to sharpen the questions before the comet re-emerges. The physics of disappearance. During this blind interval, Thrus Atlas continued on its orbit, approaching perihelion on October 29th, at a distance of 1.4 astronomical units from the Sun. That's just inside the orbit of Mars, not particularly close, but enough to flood its surface with sunlight 50% stronger than before. The temperature on its sunward face likely surged past 20 degrees, more than warm enough to sustain a torrent of water vapor jets. We can't see this directly, but models suggest that outgassing torques may be altering the comet's spin. Each jet acts like a tiny thruster, pushing the nucleus a little faster or slower, depending on its direction. For smaller comets, these effects can double rotation rates in weeks, sometimes tearing them apart. Astronomers will be watching closely in December to see whether Atlas has begun to tumble, a telltale sign that internal stresses are building. What we'll look for next. When 3i Atlas reappears from behind the Sun, in early December it will be outbound, cooling dimming but still active. The first question will be, did it survive intact? Many comets disintegrate near perihelion, their crusts splitting under heat and pressure. If Atlas has fractured, we might see twin or triple cores faintly separated each, dragging its own miniature tail. We'll also look for changes in its rotation period, shifts in jet morphology, and the evolution of the dust-to-gas ratio in its coma. Even subtle differences can reveal the internal layering of ices, whether the heating front penetrated deeper than expected, or whether the nucleus has lost significant mass. Another key target is the polarization signature. Will its bizarre negative polarization persist, or will new dust with different textures change the light's character? Every shift in reflected polarization is like a change of accent in the comet's language telling us what kind of particles are now escaping into sunlight, the observing campaign. Across the globe, observatories are already queuing up for this moment. The European Southern Observatory, the Keck telescopes in Hawaii, the Subaru telescope and numerous smaller facilities are coordinating a multi-wavelength campaign: optical, infrared, ultraviolet, and even radio. Each band of light probes a different layer of the comet's behavior. Infrared reveals temperature and dust grain size ultraviolet, catches the signature of freshly sublimated water, and radio tracks molecules like CONH3 and HCN escaping into space. The Hubble Space Telescope orbiting above Earth's atmosphere may also attempt to reacquire Atlas once its solar elongation exceeds about 50 degrees. Hubble's advantage is its stability. It can detect features faint enough to vanish in ground-based glare. Subtle jets evolving arcs of dust or the glitter of debris if the nucleus has fragmented. Meanwhile, the James Webb Space Telescope will provide something no previous mission could: infrared spectroscopy capable of identifying organic compounds and refractory ices that don't sublimate until the comet is very near the Sun. For the first time, we might glimpse complex carbon molecules, maybe even amino acid precursors, from another planetary system illuminated by ours. Citizen science and the ProAm network. Modern comet hunting isn't confined to professional astronomers. Around the world, thousands of amateur observers, skilled, patient, and equipped with small telescopes and CCD cameras, form a parallel network that can track brightness changes night by night. This ProAm collaboration professional-amateur fills the gaps between large observatories, providing continuous coverage while the big telescopes chase other targets. Many of these enthusiasts belong to organizations like the Minor Planet Center, the International Comet Quarterly, and online communities that share real-time astrometry. Their collective data often detects the earliest hints of fragmentation, a sudden brightening, a loss of symmetry in the coma, a tiny offset in position. If 3i Atlas begins to shed pieces, it's likely an amateur somewhere under a suburban sky will be the first to notice. The data pipeline is now global and nearly instantaneous. Observers upload raw measurements to shared repositories. Automated algorithms clean and standardize the values. Professionals incorporate them into models of orbital evolution and outgassing. In this way, the study of an interstellar object becomes a planetary act, a symphony of eyes across hemispheres unified by curiosity. The value of patience. Waiting through the solar blind is more than a technical necessity. It's a philosophical discipline. It reminds us that science often advances at the pace of celestial mechanics, governed not by our schedules but by the geometry of the heavens. The comet will return to view when physics allows, not when our curiosity demands. And yet that pause also sharpens the wonder. When Atlas emerges in December's dawn sky, the first images will feel almost like a reunion. We'll study its shape, brightness, and spin, comparing them to models generated during the blackout. Every pixel of data will answer a question raised during these silent weeks, or as often happens, raise new ones. Because that is how discovery works, through rhythms of light and darkness approach, and retreat presence and patience. Right now, the comet is out there unseen but not gone. It arcs behind the Sun, its nucleus cracking and steaming its tail, tracing invisible curves through the light. Somewhere in that blinding region, it continues its slow dialogue with gravity and heat carrying our questions in silence. And we wait suspended between data and imagination until the glare subsides and the sky once again reveals what the light has been hiding. December's return and Earth passage. By early December, the glare began to fade. The solar blind that had swallowed 3 Atlas for 6 long weeks slowly lifted, revealing a pale smear of light on the eastern horizon, faint at first, then unmistakable. Humanity's interstellar guest had survived its closest brush with the Sun and was now on the way out, cooling, shedding, and transforming once again. The date circled on astronomers' calendars was December 19th, 2024, the day when 3 Atlas would make its closest approach to Earth, about 1.8 astronomical units away. That's nearly 270 million kilometers too far for any chance of naked eye visibility, but close enough for the most powerful telescopes to resume detailed study. To the instruments waiting in darkness across Hawaii, Chile, and the Canary Islands, this was the return of a long-lost signal. What 1.8 AU really means. In cosmic terms, 1.8 AU is not intimacy, but opportunity. The comet would still be bright enough for large observatories to capture high-resolution spectra, yet distant enough that solar glare interference and atmospheric scattering no longer crippled observations. In the weeks surrounding that date, Earth, Atlas and the Sun would form a near-perfect geometry sunlight streaming past us to the comet, scattering back toward our telescopes. It's a favourable configuration for measuring polarization reflectivity and the changing balance of gases in the coma. Even small observatories could join in. For amateurs with CCD cameras and long focal lengths, the comet would hover near magnitude 15 to 16 invisible to the eye, but within reach of backyard astrophotography. Every image, every photon recorded would contribute to the larger picture, a world cooling down after months of heat, exhaling the last of its vapour into the void. The science of return perihelion had been its trial by fire. Now came the comparative phase, the heart of cometary science, observing the same object before and after its closest solar approach. What changes? How much mass has it lost? How does its brightness evolve once sunlight wanes? These questions turn the comet into a natural laboratory for the physics of sublimation and surface evolution. Astronomers tracked its light curve, the graph of brightness versus time, hoping to catch the gradual decline that follows every comet's peak. But they were watching for anomalies, too sudden flickers, outbursts, or plateaus that might hint at fragmentation or renewed venting from newly exposed layers. Comets often behave like living organisms, stabilizing for a while, then erupting without warning. Atlas, with its history of surprises, might yet have one more. The key was spectroscopy, the science of fingerprints. Each molecule emits or absorbs light at characteristic wavelengths. Before perihelion, 3I Atlas's spectrum had been dominated by carbon dioxide, carbon monoxide, and traces of nickel. After perihelion, astronomers expected to see a transition, stronger water lines, new metal emission, perhaps even faint bands from complex organics freed by deeper heating. In particular, they were eager to compare the H radical lines, a photochemical daughter product of water vapour, to the CO2 infrared bands measured earlier by TESS and ground-based instruments. The ratio between those two serves as a thermometer for the comet's evolution, revealing how its internal composition has changed. A surge in OH emissions would confirm that water now dominated the outflow. A persistent CO2 signal would suggest the outer crust remained cold and resistant. High-resolution spectrographs such as VLT Cryers, Keck NIRSpec, and JWST's NIRSpec were cued to capture those signals. Together they would build a before and after portrait, one side painted in carbon dioxide, the other in water and metal vapour. The differences between them would trace how sunlight migrates through the comet's layers, how heat propagates, and how volatile materials reshuffle after each solar encounter. What we hope to learn. These December observations were about more than chemistry. They were about memory. Every change in reflectance, every variation in polarization speaks to how the comet's surface has been altered, whether the once pristine crust has darkened with soot or brightened with frost. Scientists hope to see whether the extreme negative polarization seen months earlier had mellowed, implying new dust with different textures, or whether it persisted, suggesting a stable alien grain composition that even the sun couldn't erase. They also looked for shifts in the rotation period. Outgassing torques during perihelion might have spun the nucleus faster or nudged it into precession, a slow wobble that can be detected through periodic fluctuations in brightness. If the comet's light curve showed repeating pulses that would reveal both its shape and spin, giving clues to its internal cohesion. Did it survive as a single monolith, or was it cracking apart like so many smaller comets before it? And then there was the hope, faint but persistent, of catching fragments. A disintegration event would scatter shards along the comet's path, each shining briefly as its exposed ice evaporated. The Hubble Space Telescope and JWST were primed to look for such debris, their instruments capable of detecting fragments no larger than a football field. If found, they would give astronomers a rare chance to study the interior composition of an interstellar nucleus, the ultimate core sample delivered by the universe itself. A global reunion. The weeks around December 19th became a festival of observation. Professional astronomers traded data in real time through the Minor Planet Center, updating coordinates nightly as new detections refined the trajectory. Amateurs from Japan to Argentina joined in posting raw frames to shared repositories. Spectroscopists compared line intensities. Photometrists updated the light curve hour by hour. It was as though the whole planet had turned into a single rotating telescope, thousands of observers working in harmony, separated by geography but united by purpose. Each sunrise that hid the comet for one region revealed it to another. The relay of night circled the Earth, carrying the watch forward without pause. This kind of planetary collaboration is new, a direct consequence of digital connectivity and global curiosity. Astrophysics Atlas became the first truly crowd-observed interstellar object, its journey chronicled by professionals and enthusiasts alike. The data from those December nights would eventually flow into shared archives, freely available for anyone to study, proof that in astronomy, discovery has become a collective act. The meaning of distance. At 1.8 AU, no one could feel its presence. The comet's light was millions of times fainter than a candle, its shape invisible even through the largest lenses. And yet, for scientists and dreamers alike, December 19 felt like a moment of nearness. After months of silence behind the sun, the traveller had come back into view, scarred by heat, but still intact, still whispering secrets through its photons. It reminded us that closeness in astronomy is not about proximity, but about connection, about light completing its long journey to reach us. Those photons, scattered from a body forged around another star billions of years ago, had crossed the void, brushed the sun, and found their way into our telescopes and cameras. We can't touch it, but we can read it in the shifting wavelengths, the fading brightness, the dance of its rotation. Each measurement is a conversation, each image a handshake across time and space. And so, on that cold December night, Earth finally saw it again, smaller, dimmer altered, but still there, still speaking in light. A last look near Jupiter. By the time winter turned to spring 3R, Atlas was fading into the outer dark again. Its long arc away from the sun carried it past the orbit of Mars, then into the realm of the giants, that cold, beautiful province ruled by Jupiter's gravity. There, on March 16, 2026, the comet would pass within 0.36 astronomical units of the gas giant, about 54 million kilometers, close enough for Jupiter's magnetosphere to brush the faint edge of its coma. For astronomers, this encounter would be the final curtain call, the last moment when sunlight still touched the interstellar traveller, before it drifted into distances too remote for even our best instruments. But it also carried a subtle scientific prize, a chance to see how an object born around another star responds to the gravitational handshake of the largest planet in ours, the geometry of a farewell. At that distance, Jupiter would loom vast in the comet's sky, not as a sphere with bands and storms, but as a swollen disk of gold-white light 40 times brighter than any star. Around it orbited its retinue of moons, volcanic Io, icy, Europa, cratered Ganymede, and far Callisto, their shadows flickering across the clouds below. For 3I Atlas, this was the closest it would ever come to another world since leaving its birth system. The meeting was brief and silent, a matter of hours in a journey of millions of years. Yet even such a fleeting proximity has measurable consequences. Jupiter's gravity, vast and steady, is the architect of the outer solar system, the reason our asteroid belt exists, the sculptor of cometary paths. It perturbs, deflects, sometimes captures, but more often merely nods as objects pass. For an interstellar comet like Atlas, moving at tens of kilometers per second, on a hyperbolic trajectory, the deflection would be tiny. Calculations suggested that Jupiter's pull might bend its path by a fraction of a degree, enough to alter its outbound velocity by a few meters per second, no more. To us it seems almost nothing. To celestial mechanics it's a whisper of interaction, a note added to a symphony written in gravity's key. And yet that whisper is worth listening to, because every tug and turn refines our models of how interstellar objects move through planetary systems. It tells us whether these visitors are perturbed more by gas drag, by radiation pressure, or by planetary gravity. The lesson is important for the next time a traveller passes through, perhaps one we could intercept or study up close. Juno's watchful eye. In orbit around Jupiter during that season was NASA's Juno spacecraft, the solitary guardian of the gas giant. It wasn't designed to hunt comets. Its instruments are tuned for magnetospheres, auroras, and atmospheric chemistry. But Juno also carries a JunoCam, a wide-field imager used to capture the planet's swirling clouds and distant moons. For a few days around March 16th, mission scientists planned to aim it outward toward the black, hoping to catch a faint streak of light, 3I Atlas, receding from the sun. The chance of success was small. From Juno's perspective, the comet would appear only a few pixels wide, dimmer than the faintest background star. But even a single detection would be valuable. It would offer a cross-reference to Earth-based parallax measurements, a second data point confirming the comet's outbound trajectory. In celestial navigation, 2 vantage points can reveal what one alone cannot: the true curvature of a path, the minute deflection of a flyby. If the image is ever released, it will likely resemble the Perseverance photos from Mars, a smear, a glint, a faint echo of motion. But its meaning would be profound. A photograph taken by a robot orbiting Jupiter, looking out into interstellar space at a comet from another star. Gravity's gentle hand. To the human imagination, Jupiter's pull feels immense. It's more massive than all the other planets combined, its magnetic field extends millions of kilometers, and its influence shapes the orbits of asteroids across the solar system. But scale changes everything. For a visitor like 3I Atlas, moving at escape velocity from the Sun, roughly 58 kilometers per second, even Jupiter's gravity is but a touch on the shoulder. The equations of orbital dynamics show why. The comet's energy relative to the Sun is positive, it's unbound, already free. Jupiter's attraction can nudge it but not capture it. The result is a minuscule deflection, a soft curvature in the outbound leg of its hyperbola. To an artist, it's the difference between a straight line and a barely perceptible arc. To a scientist, it's confirmation that the laws of gravity hold perfectly, even for something that has traveled for billions of years through alien skies. If this encounter were a dance Jupiter led with patience, it didn't seize the partner, only guided it slightly toward the outer dark. After that, 3I Atlas would never return. The Sun's pull would weaken, the light would fade, and its orbit would flatten into near straightness and escape back into the vast galactic night. The poetry of goodbye. There's a certain grace in that moment, a comet from another star passing the mightiest world of ours, exchanging no more than a gravitational nod. It's like 2 ships crossing in the same current, each immense in its own way, their wakes briefly mingling before diverging forever. From Earth, the event was invisible, hidden behind distance and darkness. Yet we can imagine it, the thin trailing ribbon of the comet glimmering in faint sunlight, Jupiter's storms swirling far below Juno, orbiting like a silent witness between them. For a heartbeat of cosmic time, 3 worlds, one, native one, mechanical one, interstellar, shared the same quadrant of space. After that, 3I Atlas would slip into invisibility for good. Its gases would freeze again, its tail would collapse into dust. It would become what it had always been, a dark traveler carrying the memory of another star. Still, the physics leaves room for poetry. Every time a comet passes a giant planet, their paths bend infinitesimally toward or away threads, weaving the larger tapestry of galactic motion. Even the smallest deflection means the Sun's family has left a mark, a trace of its gravity inscribed on the orbit of a stranger. So when 3I Atlas brushed past Jupiter that March morning, it wasn't just a maneuver in space. It was a farewell handshake between systems, the visitor acknowledging the host letting go. After that, nothing bound it to us anymore. And somewhere within that faint arc, measured in fractions of a degree, lay the difference between staying and going, between belonging to one star and returning to the silence between them. Part 23. What strangeness teaches normality? By the spring of 2026, the Delta was in. Spectra-like curves and images from every phase of 3I Atlas's visit, from its pre-solar awakening to its fading near Jupiter, had been combined, cross-checked and modelled. What emerged wasn't a tidy story, but a portrait of strangeness, contradictions held together by physics we only half understand. It began with polarization, the way sunlight scattered off the comet's dust, producing the most extreme negative polarization ever recorded. It suggested grains unlike anything seen before, porous, complex, perhaps glassy, perhaps metallic, each scattering light not as smooth spheres, but as fractal clusters. Then there was the early CO2 activity, long before the warmth of the inner system could have triggered it. That told us the ices were unusually volatile, perhaps layered with dry ice and exotic compounds preserved from a colder birthplace. Next came the nickel-iron riddle, nickel lines, bright weeks before iron joined in. And finally, the sunward tail, a dust sheet appearing to defy the very direction of sunlight itself. Each anomaly alone could be dismissed as a curiosity, an outlier, within the range of cometary behaviour. But together they formed a pattern not of error, but of difference. 3I Atlas was telling us in the language of light and motion that the chemistry of worlds is broader than our solar imagination allows, the architecture of alien ice. In the controlled cold of laboratories on Earth, scientists have begun to recreate the ices thought to form in protoplanetary disks, mixtures of water, carbon monoxide, methane, ammonia, and carbon dioxide frozen together at temperatures near absolute zero. When irradiated by ultraviolet light or cosmic rays, these ices evolve, bonds break atoms, rearrange, and new molecules form, some simple, others startlingly complex. The result is not uniform frost, but chemical topography layers and clumps with different densities, colours and volatilities. 3I Atlas fits this picture perfectly. Its early CO2 outgassing beyond 5 astronomical units implies that its surface retained high volatility ices materials that would have sublimated away long ago in most comets born near our Sun. That means its parent system must have had a colder outer region, perhaps, with a weaker star or a different balance of radiation and disk density. Its mantle wasn't a thin crust over water ice, but a stratified relic of formation, a chemical palimpsest that responded to heat in the order of its birth. When heat reached the surface, CO2 went first, creating those ghostly pre-perihelion jets. Only later did the deeper water-rich layers crack open, producing the violent reversal we observed near 1.5 AU, the fire hose of vapor that redefined the comet's coma. That sequence tells us the temperature gradients, permeability, and grain cohesion of this body are profoundly unlike those of our solar comets. The metallic whisper. The delayed dance of nickel and iron remains perhaps the most evocative clue. Laboratory vaporization of silicate dust under simulated comet conditions shows that micron-scale grains containing metallic inclusions can fractionate nickel oxides, sublimating slightly earlier iron compounds holding out longer. In Earth's comets, those effects are often masked by overwhelming water-driven outflow, but in Atlas the weaker early jets and the alien chemistry amplified them. The result was an observable imbalance, a chance to watch elemental separation in real time, something models had predicted but never caught in nature. It implies that Atlas's dust grains were chemically differentiated on scales of microns to millimeters, a sign of slow condensation and gentle aggregation in its natal disk. That's a disk where metallic vapors condensed under lower pressures and weaker magnetic fields than those that birthed our own sun's planets. Light that lies and reveals. Then came the light. The comet's negative polarization was so deep that even finely tuned models struggled to reproduce it. In the lab, only the most fluffy aggregates of submicron grains, like microscopic snowflakes of carbon, soot, and glassy silicates, produced that effect. They scatter light in strange ways, absorbing rather than reflecting at certain angles, flipping the polarization vector backward. To create such grains requires not collisions but slow coagulation in dense, quiescent clouds, environments rich in organic vapors and low in turbulence. In other words, 3I Atlas wasn't forged in a violent nebula like ours, but in a quieter nursery, perhaps around a smaller, longer-lived star. Its very dust was born in calmness, fragile, airy, nearly weightless, the texture of cosmic stillness. The tail that bent toward the light. Even the anti-tail, that temporary sunward illusion, speaks to environmental conditions. Large, heavy grains aren't easily swept away by the solar wind unless that wind is strong. In 2025, the sun's wind was weaker than average, a quirk of the solar cycle, allowing Atlas's coarse, slow-moving dust to linger and form that sunward fan. But those grains had to exist in the first place, millimeter-sized fragments, dense enough to resist radiation pressure. Their presence suggests that Atlas's surface crust was tough, cohesive, and rich in refractory material, more like a cemented rock than a fragile snowball. Together, these details sketch a comet that is neither fully icy nor fully dusty, neither fragile nor dense, but something in between, a hybrid of delicacy and endurance. It is as if Atlas condensed in a system where the chemistry of metals, organics and ices mixed differently under different heat gradients and disk pressures. Redefining normal. For decades, we've treated our own solar comets as templates for all others, the benchmark of how planetesimals form. 1 Oumuamua and 2I Borisov cracked that assumption. 3I Atlas has now shattered it entirely. Its anomalies force modelers to widen the range of parameters they simulate, not just the ratios of ice to dust, but the microstructure of grains, the volatility hierarchy of ices, and the radiation history of their parent stars. In the new models being tested, disks around cooler stars produce comets rich in carbon dioxide and carbon monoxide. Disks near hotter stars favor water and silicates. Magnetic fields alter how metals condense, shaping whether nickel and iron segregate or blend. Even local cosmic ray flux, the invisible drizzle of particles from nearby supernovae, can carve subtle differences into ice chemistry. 3i Atlas becomes in this light not an exception, but a data point on a universal spectrum. It teaches us that normal is simply what happens here. Elsewhere, the same physical laws play out under different balances, yielding other textures, other chemistries, other kinds of worlds. The human lesson in the data. The deeper lesson is philosophical as much as scientific. For centuries we've assumed the cosmos repeats itself, that the planets, comets and elements we know are representative. Atlas suggests a subtler truth: diversity is the rule, uniformity the illusion. The anomalies aren't noise, they're invitations to expand our definition of order. Each irregularity widens the range of what possible means. A tail pointing the wrong way, a metal glowing alone, an ice that wakes in the cold. These are not mistakes in the universe's grammar, but variations in its dialect. We study them not to normalize them, but to enlarge the idea of normal. And so in laboratories chilled to near zero, scientists now reproduce the comet's strange polarizations, its asymmetric jets, its spectral fingerprints. In supercomputers, they rerun the physics of disk formation with new variables, slower rotations, weaker magnetic fields, cooler suns. In the data, they search for the signature of quiet systems, the galactic neighborhoods where objects like Atlas might be common, even ordinary. If we could step back and see all those planetary cradles at once, we might find that the real anomaly is us, the warmth of our sun, the dryness of our comets, the chemistry of our skies. 3i Atlas was strange, only because we hadn't yet seen enough of the universe to realize how wide normal truly is, how surveys changed our nights. Before the 21st century, the sky was mostly silent between discoveries. Astronomers pointed narrow telescopes at chosen targets and waited for chance to deliver surprise. Comets came and went, asteroids passed unnoticed. Novae flared unseen except by those lucky enough to look up at the right time. But that silence was an illusion. The heavens were always busy. It was we who were blind. Then quietly the instruments changed. Wide-field cameras began to patrol the night with machine patients taking hundreds of images every hour, comparing them pixel by pixel. Out of that constant vigilance came a new kind of astronomy, one not of singular events, but of continuous awareness. 3i Atlas. The comet whose story we've followed exists in our knowledge because of this shift. The eyes that never sleep, the asteroid terrestrial impact last alert system. Atlas is not one telescope but 4 stationed in Hawaii, Chile and South Africa. Each unit scans the whole sky several times a night looking for motion. Its mission began as planetary defense spotting potentially hazardous asteroids, but it became a gateway for cosmic serendipity. When it flagged a moving object on July 1st, 2025, no one knew it was interstellar. The algorithm simply did its job: subtract one image from another, find the difference, check the motion, and raise a flag. That quiet sequence exposure subtraction alert has revolutionized discovery. What used to depend on human luck now happens through algorithmic attention. Machines don't blink. They compare tens of terabytes nightly cross-matching, with catalogs filtering out noise from cosmic rays, satellites, and camera defects. And when something doesn't fit, something that moves too fast, too oddly, it goes to a human. The humans who listen. This is the part most people never see: the global network of astronomers, graduate students, and even amateur skywatchers who wake to alerts and start verifying. They check follow-up observations, confirm trajectories, and refine orbital parameters before dawn. In the case of 3i Atlas, confirmation came within hours, because observers on 3 continents responded to the call. A signal in Hawaii became coordinates in South Africa, became a trajectory in Chile, a relay of midnight heroics stitched together by curiosity. This is what modern discovery looks like: not a lone observer at an eyepiece, but a distributed civilization watching itself through the sky. The age of the infinite feed. Above all, the Atlas detections signaled the arrival of a new kind of instrument, the all-sky feed. Just as social networks scroll through lives, these robotic telescopes scroll through the cosmos, capturing change as it happens, a living record of motion, brightness, and transience. The TESS satellite, built to hunt exoplanets, plays its part too. By staring at large patches of the sky for weeks at a time, it creates time-lapse portraits of brightness that catch not only planets, but also comets, novae, and even the dim trails of interstellar wanderers. When scientists found 3I Atlas in its archival images from May 2025, they coined a new word for the process precovery, a discovery made retroactively proof that we often see things long before we recognize them. Precovery symbolizes the new rhythm of astronomy. We no longer just look forward, we mine the past. Every frame ever taken by any telescope becomes part of a searchable memory of the universe. When new objects appear, algorithms crawl back through that archive, connecting forgotten pixels into coherent histories. Enter the era of deluge. And yet this is only the beginning. In northern Chile, on a dry plateau beneath the Andes, stands the nearly completed Vera C. Rubin Observatory, home of the Legacy Survey of Space and Time LSST. When its 8.4-meter mirror opens fully to the night, it will take panoramic images so vast that each frame could fill a wall. Every 30 seconds, another exposure. Every few nights, the entire visible sky mapped anew. The numbers are staggering: 20 terabytes per night, billions of stars and galaxies catalogued, millions of moving objects detected, every flicker, every flare, every drifting rock. It will turn astronomy into a form of real-time storytelling, a constant stream of events from asteroids to supernovae erupting across data feeds like breaking news. To handle that, scientists have trained neural networks to recognize the unexpected, to know what normal sky behavior looks like, so that when the strange appears, it stands out. These are the machine apprentices of human curiosity, designed not to replace our wonder, but to scale it. The quiet heroics of connection. Behind each alert lies an invisible chain, programmers writing code to correct camera drift, technicians aligning optics under freezing skies, students sorting false positives until dawn. And then there are the amateurs, the enthusiasts with backyard telescopes and determination, who answer those alerts, uploading follow-up images that confirm or refute a transient. When 3I Atlas appeared, some of the earliest verifications came not from major observatories, but from small community setups, telescopes no larger than dining tables, guided by software freely shared online. Each pixel they contributed helped triangulate the comet's path. In the databases, their names sit beside those of professionals' equal entries in a global log of discovery. It's a quiet revolution citizen science woven into the fabric of high-precision astrophysics. The line between hobbyist and professional has blurred, replaced by collaboration across bandwidth and time zones. The cosmos no longer waits for approval. It simply reveals itself to whoever is listening. Seeing the sky as one continuum. What we learn from 3I Atlas and from the era that found it is that the universe has become a shared canvas. Every image feeds into a collective consciousness of the sky. No single observer owns a discovery. We all participate in the act of noticing. In that sense, telescopes like Atlas TESS and soon Rubin are not just instruments, they are extensions of human awareness. Mechanical eyelids that open and close through the night, capturing the ceaseless conversation between matter and light. Their data will teach us to see variability not as noise, but as the pulse of existence. Comets, flares, transits, collapses, each one a heartbeat in a cosmos alive with motion. The night that watches. Back. The phrase all-sky survey sounds technical, but it hides a quiet poetry. It means that the heavens are now being watched everywhere all the time, not out of paranoia, but out of devotion. We built machines to look up for us because we couldn't stay awake forever, because wonder needed endurance. And in that endurance, the universe has started to answer. Sometimes with comets that come from other suns, sometimes with stars that blink to reveal new planets, sometimes with data so vast we need algorithms to feel awe for us until we can catch up. When you step outside on a clear night, remember somewhere on a mountaintop or in orbit, a camera is taking a picture of the same sky, quietly, methodically ensuring that nothing escapes notice. 3 Atlas was one story drawn from that vigilance. The next may already be glowing unnoticed in tonight's images, waiting for dawn, and for someone somewhere to look closely enough to say, there, something moved. Ghosts of visitors past. Every new arrival changes the way we remember the old ones. When 3 Atlas entered our solar system, it carried not only its own mystery, but the long shadow of its predecessors, two ghosts still drifting in the imagination of science. Oumuamua and 2I Borisov. They were the first proof that interstellar objects are not rare, only rarely seen. But they were also reminders of how fragile our certainty can be, how quickly curiosity can slide into conviction, and how long it takes for patients to correct the story. Oumuamua, the misunderstood messenger. It began in 2017 with a faint, fast streak across the Pan-STARRS sky survey in Hawaii. The object that would be called Oumuamua Hawaiian for scout or messenger from afar was already leaving by the time we noticed it. Long, tumbling and oddly reflective, it accelerated slightly as it exited the solar system. No coma, no gas yet, something was pushing it. For months, telescopes followed it, but every observation deepened the confusion. It looked like a rock, but moved like an ice fragment. It behaved like a comet, but without the visible tail. Hypotheses multiplied a pancake-shaped shard of nitrogen ice, a fluffy fractal of dust, a hydrogen iceberg, an alien light sail. Each model explained something, but broke something else. In the years that followed, we learned to live with uncertainty. The acceleration could be explained in part by outgassing too subtle for our instruments to see. The shape might not have been cigar-like at all, but flat and irregular, a product of biased data sampling. The brightness variation might have been caused by tumbling geometry, not alien design. But perhaps the most important lesson was not what Oumuamua was, but how we reacted to it. We wanted it to be exceptional, the herald of a cosmic contact. We filled the silence of data with imagination. The real revelation came later, that even extraordinary behavior can emerge from ordinary physics when observed from the wrong angle with incomplete instruments. Oumuamua reminded us that the absence of evidence is not evidence of absence, but neither is it license to invent. Between those two extremes lies the narrow path of science, the patience to let data accumulate until clarity emerges naturally without force. Borisov, the ordinary miracle. 2 years later, in 2009, to Im Borisov arrived a gift of contrast. Discovered by amateur astronomer Gennady Borisov using a home-built telescope in Crimea, it looked immediately familiar. A bright nucleus, a wide tail, the unmistakable glow of vaporizing ice. Where Oumuamua was elusive and silent, Borisov was generous, and textbook clear a comet in every sense except that its orbit was hyperbolic, its speed interstellar. Its spectra revealed cyanide water and carbon monoxide in roughly the same ratios as comets from our own solar system. For all its exotic origin, Borisov felt comfortingly normal, and that normality was profound. It proved that other planetary systems produce the same kinds of ices, the same chemical recipes, the same building blocks of worlds. When astronomers studied its dust grains, they found them porous, fluffy, and rich in carbon, the fingerprints of slow growth in a cold outer disk. It was as if we had plucked a snowball from another star and found it almost indistinguishable from ours. The patience between them, between Oumuamua and Borisov, between anomaly and familiarity, science learned balance. The first taught humility, the danger of overreading the unknown. The second taught patience, that waiting for the next visitor can transform speculation into understanding. 3i Atlas, arriving years later, completes that trilogy not by resolving the mysteries but by reframing them. It shows that both extremes, the too weird and the comfortably normal, are part of the same cosmic spectrum. Oumuamua's ambiguity and Borisov's familiarity are no longer contradictions. They're bookends to the diversity of interstellar debris. Cumulative wonder science is not a series of shocks, but a slow accumulation of precision. Each visitor adds a line to the ledger, the reflectivity, the polarization, the volatility, the composition. In time, patterns will emerge not because of a single breakthrough, but because of the gentle persistence of watching. Already computer models have begun to connect the dots. Simulations show how planetesimals ejected from young systems scatter into the galaxy by the billions, drifting for eons before brushing another star's gravity. We now expect that at any given moment, hundreds of interstellar fragments are passing through the outer solar system, faint and unseen. Oumuamua was the first whisper. Borisov was the confirmation. Atlas, the deepening of the chorus, the discipline of humility. There is a quiet virtue in admitting we do not know yet. Each of these objects arrived uninvited, stayed briefly, and left more questions than answers. But the act of watching carefully, collectively, without surrendering to drama, transforms those questions into progress. It's tempting to see Oumuamua as a missed chance, the one that got away, Borisov as the safe one, Atlas as the strange one. But the deeper truth is that science matures through repetition. One event inspires a theory, 2 test it, 3 begin to map a landscape. In that light, 3 Atlas is not an isolated marvel but a continuation and a data point in a widening field of understanding that stretches from the 2017 skies of Hawaii to the telescopes of 2026 and beyond. The ghosts of visitors past still move with us. Each new detection reinterprets their memory, refines our models, reshapes our humility. What once looked alien now seems plausible. What once looked familiar now hides new subtleties. And in this gradual, cumulative awakening, science itself becomes what it has always been at its best. Not a gallery of certainties, but a cathedral of patience, where every observation is another brick laid in the long, slow construction of truth. The comet as a mirror. By the end of its journey through our skies, 3 Atlas had become more than an object of study. It was a mirror held quietly against the human mind. We had measured its trajectory, its spectra, its light curve. But in the reflections of that data, we could also see ourselves, our instinct to seek pattern, our need to tell stories when the dark feels too vast, our longing to connect what we can't touch. Every civilization that ever looked up at a comet has faced this same impulse. Before equations, before telescopes, there was only wonder shaped into narrative. Ancient eyes shared sky. In ancient China, comets were broom stars, celestial sweepers brushing away dynasties or cleansing the heavens of corruption. In Greece, Aristotle believed they were fiery exhalations from Earth's atmosphere rising and burning in the sky. The Maya carved them into their stelae as portents of change. In medieval Europe, chroniclers sketched them beside plagues and coronations. Each story in its own way tried to make the unpredictable bearable. A sudden streak in the night sky was too beautiful, too ungoverned to leave unnamed, and so people named it, and by naming made it theirs. When 3 Atlas appeared, our myths were scientific ones: comet, interstellar object, hyperbolic visitor. Yet the instinct was the same. We reached for meaning, and in doing so revealed our continuity with the watchers who came before. The labels changed, but the awe remained a shared reflex across millennia, from shepherds in Sumer to graduate students in Hawaii. The gift of ambiguity comets have always demanded humility. They appear suddenly, disobey expectations, and fade just as fast. They belong to that small class of phenomena like dreams, like love, like consciousness itself, that resist tidy explanation. 3 Atlas, with its contradictory behavior and alien chemistry, invited not just analysis but introspection. It asked in its silent passing, what do you do when the facts remain incomplete? Do you fill the gaps with fear, with invention, with patience? We live in an age that fears uncertainty. Every unanswered question becomes a headline, every anomaly a conspiracy. But 3 Atlas offered a gentler lesson. Ambiguity is not chaos. It's the space in which imagination and evidence learn to coexist. It's the calm between discovery and understanding, the pause that makes science human. When astronomers spoke honestly of not knowing of flux ratios that made no sense of polarization, that defied expectation, they modeled something precious, the courage to stay with the question. In that courage lies the heart of both science and philosophy. A night that unites. Across continents, people followed updates not because they feared collision, but because they felt kinship. In forums and message boards under clear or cloudy skies, strangers compared observations. Faint glows through backyard telescopes, live feeds from observatories, sketches made by hand. It was a modern form of an ancient ritual, the night watch. Once it was a fire on a hillside, now it's a broadband connection, a shared graph of brightness, a collective breath held under the same stars. There's something profoundly democratic about that. The sky belongs to everyone. Whether you watch it from a desert, a city rooftop, or a dormitory window, it offers the same canvas. No one owns the comets, yet they unite us more reliably than any broadcast. Stories as instruments of balance. The narratives we build around such objects are not weaknesses of science. They're the emotional scaffolding that lets us engage with scales too large to comprehend. We tell stories not to replace data, but to anchor ourselves within it. 3 Atlas gave us data that stretched across billions of years and light years of space, and so instinctively we translated it back into human rhythm, a visitor, a journey, a return to the dark. We made it a story because the mind needs cadence to find meaning, and perhaps that's what science truly is, a long, slow story, told in careful increments with footnotes instead of verses, yet driven by the same pulse that once drew poets to the stars. Science for sleep. When the work is done, when the last spectra have been plotted and the comet has faded, we return to the simple act of looking up. The night becomes a quiet laboratory for reflection. In the soft hours before dawn, when even the observatories fall silent, we feel the rhythm that all watchers share, curiosity dissolving into calm. That is the cadence of science for sleep. Reminder that knowledge and peace are not opposites. That to understand the universe is not to conquer it, but to rest inside its vastness without fear. Thrusison's atlas has left us now, but its wake lingers in the archives, in the stories, in the quiet awareness that every object we study also studies us, if only by reflecting what kind of beings choose to notice. It is gone, yes, but the habit of wonder remains, and perhaps that's what comets are, for not to tell us where we're going, but to remind us how to keep looking while we wait. When mystery is a teacher, in the end, perhaps 3E Atlas was never meant to give us answers. Perhaps its true purpose, if nature can be said to have one, was simply to remind us how to ask better questions. The data will continue to arrive for years. Spectra archived, orbits refined, models adjusted. In time, scientists will decide that the comet's chemistry fits some broader pattern, that what seemed strange here may be common elsewhere. And when that happens, the world will nod and move on. Another object, another anomaly tamed. But those who stayed awake through the nights of its passing will remember something that can't be catalogued, the feeling of discovery still unfolding. Because that's what 3i Atlas taught most of all, that mystery itself has value. Not as a placeholder for ignorance, but as a teacher of patience, humility and awe. The grace of not knowing. Every orbit, every equation, every photon caught by a telescope was an act of trust. Trust that the universe is intelligible even when it withholds clarity. The astronomers who tracked 3i Atlas through the blinding glare of the sun, the engineers who tuned sensors in midnight domes, the amateurs who uploaded images from quiet backyards, all of them shared in that trust. They did not chase certainty, they tended to wonder. In their vigilance, there was gratitude for the instruments that extend our senses, for the collaborations that bridge continents, for the rare gift of a mystery big enough to make us feel small again. Science at its heart is not a conquest of nature, but a conversation with it. And conversations require listening. 3i Atlas reminded us how to listen to the faint delayed echo of photons scattered across space, to the silence that follows an unanswered question, to the whisper of humility between data points. The watchers. Somewhere in Hawaii, a telescope dome closes with a hydraulic sigh. In Chile, a graduate student uploads the final light curve. On Mars, the Perseverance rover's camera lens gathers a trace of dust, the same dust that once caught light from a comet now far beyond Jupiter. The watchers go home, the servers hum, and the sky resets itself. Each of them, knowingly or not, has participated in a kind of prayer, a secular devotion to the act of noticing. It is easy to forget that behind every graph there is a human heartbeat, behind every algorithm a pair of eyes that once stared upward as a child. 3i Atlas rekindled that connection, the quiet realization that the work of watching the universe is also the work of remembering why we care. The long wait now. The object drifts outward dimmer each week until even the largest telescopes lose it. The coordinates will remain in databases, the designation 3i Atlas preserved in catalogues. But its physical light, the photons that once touched it, will fade beyond recall. And yet the waiting does not end. We know there will be others, more visitors on hyperbolic paths, each carrying a different accent of matter, each reminding us that the galaxy is not empty, but in conversation with itself. We will watch again, measure again, wonder again. That is the rhythm of this new astronomy discovery, followed by uncertainty, by analysis, by silence, by renewal. The sky exhales, we inhale, the dialogue continues, the soft breath of wonder. If you step outside now, wherever you are, the sky above you holds no visible trace of 3i Atlas. And yet knowing it passed through changes the way darkness feels. The stars seem nearer not because they moved, but because our attention did. That's what these stories and this slow science are for. To reawaken attention. To make mystery feel like home again. So we close this journey not with conclusions, but with gratitude for the watchers who stayed awake. For the instruments that never blinked. For the patience that turned data into meaning. And for the mystery that refused to resolve itself too quickly, so that we might linger here a little longer, suspended between knowledge and wonder. Take one last breath with it, slow, deliberate. Imagine the comet receding, the sunlight fading from its ice, the silence returning to its path. And as it slips back into the dark between stars, remember, perhaps the universe teaches not by giving us answers, but by keeping us awake to ask. Thank you so much for keeping me company tonight. Don't forget to subscribe so we can share many more stories together.